Hey friends, welcome back to Sleepy Science. Before we dive into tonight's cosmic journey, I need to tell you about a moment that happened on March 30th, 2020, that nearly broke the hearts of everyone at NASA's Jet Propulsion Laboratory. It was 11.5 billion miles away from Earth. Voyager 2 had just gone silent. For the first time in 18 years, the antenna that connected us to this lonely traveler had stopped listening. Engineers stared at their screens, knowing that somewhere in the darkness beyond Neptune, beyond the edge of our solar system, a machine was calling out to us, and we couldn't hear it. The last command they sent? Goodbye, old friend. We'll talk again in 11 months. But here's what terrified them. Voyager 2 wasn't designed to survive 11 months without contact. It was designed to survive 5 years. And it had already been flying for 43. If you're curious about how a machine from the 1970s is still alive in the deadliest environment imaginable, and why its survival might be the most important thing humanity has ever achieved, hit that like button and subscribe, because what you're about to discover will change how you see not just space exploration, but what we're capable of as a species. Now, I want you to imagine something with me. Picture the most isolated place on Earth. Maybe it's the middle of the Pacific Ocean, or Antarctica, or the peak of Everest. Got it? Now multiply that isolation by 1 billion. That's not even close to where Voyager 1 is right now. As I'm speaking to you, Voyager 1 is 15 billion miles from home, moving through a region of space so empty, so cold, so hostile, that nothing we've ever built was meant to survive there. And yet, every single day, this probe built when your grandparents were young, when computers had less power than your car key fob, when people still used rotary phones, sends us a signal, a whisper across the cosmic void that says, I'm still here, I'm still working, I'm still discovering. August 20th, 1977. Voyager 2 launches from Cape Canaveral on a Titan Centaur rocket. The mission objective, fly by Jupiter and Saturn, take some pictures, maybe last 5 years if we're lucky. September 5th, 1977. Voyager 1 follows 16 days later, but on a faster trajectory. These weren't meant to be immortal. They were built for a brief tour of the outer planets, then nothing. Silence, the endless dark. NASA engineers gave them a 5-year life expectancy. The plutonium power source? Maybe 12 years if it was exceptional. The instruments? They'd probably fail long before that from the intense radiation near Jupiter. But here's where it gets interesting. Someone on that team, probably lying awake at 3 a.m., asked a dangerous question. What if they don't die? What if, against all odds, these machines survived longer than anyone dreamed? What would they tell us about the universe beyond our solar system? That question led to some of the most beautiful over-engineering in human history. They didn't just build Voyager to last 5 years. They built it like they were building forever. Let me paint you a picture of what's happening right now, this very second. Voyager 1 is traveling at 38,000 miles per hour. That's New York to Los Angeles in 4 minutes. It's been doing this for 47 years straight. No stops, no maintenance, no software updates really, just flying. By the time its radio signal reaches Earth, it's been traveling for over 22 hours at the speed of light. Think about that. Light itself, the fastest thing in the universe, takes almost a full day to make the journey from Voyager to your screen. When we send a command to Voyager 1, it takes 22 hours to get there. And if something goes wrong, another 22 hours before we know. That's a 44-hour conversation delay. Imagine texting someone and waiting 2 days for a response, then 2 more days to say, oops, I meant something else. But here's what makes this truly mind-bending. In 2012, Voyager 1 crossed a boundary no human-made object had ever reached, the heliopause, the edge of our sun's influence, the place where the solar wind, that stream of particles flowing from our star, finally stops pushing, and the interstellar medium begins. Voyager 1 became the first ambassador of Earth to venture into the space between the stars. And its instruments, built in the 1970s with technology that couldn't even play a CD, detected this transition. It measured the change. It told us what interstellar space feels like. Voyager 2 followed in 2018, crossing at a different location, giving us a second data point. And here's what shocked everyone. The two crossing points were different. The boundary isn't a clean line. It's ragged, dynamic, breathing like a living thing. Without Voyager, we'd never have known. All our theories, all our models were incomplete. Two machines that should have been dead for 3 decades just rewrote the textbooks on where our solar system ends. Now, let me take you back to that moment in 2020, March 30th. The Deep Space Network antenna in Australia, the only one that could talk to Voyager 2, needed urgent upgrades. They'd been putting it off for years, but it couldn't wait anymore. The 70-meter dish was 48 years old. Parts were failing, so they shut it down. For 11 months, they would upgrade everything. New transmitters, new receivers, new control systems. And during that time, Voyager 2 would be completely alone. No one listening, no one able to send commands if something went wrong. The team ran the numbers. Voyager 2's power levels were dropping by about 4 watts per year as its plutonium decayed. Its instruments were barely hanging on. One by one, heaters had been turned off to conserve power. The spacecraft was essentially freezing itself to stay alive, running colder than it was ever designed to operate. If anything critical failed during those 11 months, if a cosmic ray hit just the wrong component, if the attitude control system glitched and the antenna pointed away from Earth, that would be it. Game over. No rescue possible. The last transmission before silence was loaded with diagnostic data. Every system status, every temperature reading, every voltage level. Engineers analyzed it like doctors reading a patient's chart before a risky surgery. And then they sent one final command sequence, a script that would guide Voyager 2 through the next 11 months autonomously. Fire these thrusters on this date to maintain orientation. Switch to this backup system if temperature drops below this threshold. Keep the antenna pointed at Earth no matter what. Then they pressed send and waited 19 hours for confirmation that Voyager received it. When that confirmation came back, Susan Dodd, the Voyager project manager, later said it felt like watching your child leave for college, except your child is 11.5 billion miles away and you can't call them. Those 11 months were agony. Every day, engineers would imagine worst-case scenarios. What if the power system failed? What if the computer reset and lost its orientation? What if after all these years, this was how it ended? Not with a bang, but with silence while we weren't listening. November 2020. The Australian antenna comes back online. The team loads the first command. Voyager 2, are you there? 19 hours to reach, 19 hours to return, 38 hours of holding their breath. And then, streaming through the receivers, a signal. Weak, incredibly weak, but steady. Voyager 2 responded. It had survived completely alone, in the dark, following instructions uploaded 11 months earlier. Not only had it survived, it had thrived. All systems nominal, all instruments functioning. It had even performed a course correction autonomously, exactly as programmed. Do you know what the odds of this were? Building a machine in 1977, launching it into the most hostile environment imaginable, and having it not just survive, but excel 43 years later? Engineers I've spoken to say it's like throwing a paper airplane from Los Angeles and having it land perfectly on a postage stamp in New York. Then having that paper airplane call you to say, it's doing great. It shouldn't be possible. Every law of probability says this machine should be dead. Every historical precedent says complex technology fails, especially in space. The moon rovers died after a few years. The Mars Opportunity rover, which we celebrated lasting 15 years, is a baby compared to Voyager. An Opportunity had solar panels that could theoretically provide power forever. Voyager is running on a slowly dying nuclear battery that will eventually, inevitably run out. Here's what keeps me up at night in the best possible way. Right now, at this moment, both Voyagers are out there. Voyager 1 has been silent since November 2023 due to a computer glitch, but engineers are working to revive it. Voyager 2 is still talking, still sending data about the interstellar medium, about cosmic rays, about magnetic fields in regions of space we've never measured. These machines are our most distant explorers, our most remote outposts, our furthest reached fingers touching the universe. And every day they survive is a gift we didn't expect and barely deserve. So, why does this matter? Why should you care about two old spacecraft that most people have forgotten about? Because Voyager is proof. Proof that when we commit to something larger than ourselves, when we build not for profit or for glory, but for pure discovery, we can create something that outlasts us. Everyone who built Voyager, who welded its parts, who wrote its code, who designed its circuits, most of them are retired now, some have passed away. But their work is still out there, still functioning, still teaching us. That's immortality, not through children or wealth or fame, but through contribution to human knowledge that echoes through decades and will echo through millennia. In about 5 to 10 years, both Voyagers will go silent forever. Their plutonium will decay past the point of generating enough electricity. One by one, instruments will shut down. The transmitter will flicker and die. And then they'll just float forever. They'll orbit the center of our galaxy every 225 million years, silent witnesses to the universe, carrying their golden records with sounds and images of Earth. In 40,000 years, Voyager 1 will drift within 1.6 light-years of a star called Gliese 445. In 296,000 years, Voyager 2 will pass within 4.3 light-years of Sirius, the brightest star in our night sky. And they'll keep going. Billions of years from now, when our sun has swelled into a red giant and consumed the Earth, when humanity is either extinct or scattered among the stars or transformed into something we can't imagine, Voyager will still be out there. The last surviving evidence that we existed, that we dreamed, that we reached out into the dark because we had to know what was there. But before they go silent, before that final transmission, we need to understand how this miracle happened. Because Voyager isn't just a story about technology. It's a story about a cosmic opportunity that only comes once every 176 years, about politicians who almost killed the mission before it launched, about engineers who refused to accept good enough, and about a dream so audacious that even the people who proposed it thought it was impossible. The question that haunts everyone who knows this story: how did we get so lucky? How did everything align perfectly for these machines to survive when they shouldn't have? The answer begins in 1965, when a young aerospace engineer named Gary Flandreau was crunching numbers at NASA's Jet Propulsion Laboratory and discovered something that would change history. He found a window, a brief, precious window in time where all the outer planets would align in such a way that a single spacecraft could visit them all using a technique called gravity assist, where each planet's gravity would slingshot the probe to the next, requiring almost no fuel. This alignment happens once every 176 years. The last time it happened, Abraham Lincoln wasn't even born yet. The next time it will happen, we'll all be long gone. But discovering this alignment was just the beginning. Because in the Cold War era of tight budgets and political pressure, convincing the government to fund a mission to the outer planets, a mission that would take over a decade just to reach Neptune, a mission that wouldn't produce results until long after the politicians who approved it had left office, seemed impossible. The story of how Voyager almost died before it even launched, how it was saved by cleverness and determination and a bit of political theater, that's where we're headed next. Summer of 1965. A 25-year-old aerospace engineer named Gary Flandreau sits in a small office at NASA's Jet Propulsion Laboratory in Pasadena, California. He's been given what seems like a mundane assignment: calculate possible trajectories for missions to the outer planets. He's punching numbers into a mainframe computer, plotting orbits, when suddenly his pencil stops moving. He stares at his calculations. Then he checks them again. And again. Because what he's seeing shouldn't be possible. According to his math, in the late 1970s, all 4 of the outer planets, Jupiter, Saturn, Uranus, and Neptune, would align in such a way that a single spacecraft could visit every single one of them. Not 4 separate missions. 1 spacecraft, 1 launch, 4 planets. And this alignment happens once every 176 years. If you want to see how a cosmic accident, a political nightmare, and the stubbornness of a few brilliant engineers created the greatest space mission in history, stay with me. Because what I'm about to share will show you that Voyager almost never happened, and the reasons why will make you question how any great thing ever gets done. Let me take you back to what Flandreau actually discovered, because it's more beautiful than most people realize. Imagine you're trying to visit 4 cities, but you don't have enough gas money for the trip. Now imagine if those 4 cities happen to line up perfectly on one highway. And not only that, but each city has a giant slingshot that flings you toward the next one, faster than you arrived. That's essentially what Flandreau found, except instead of cities and slingshots, it's planets and gravity. The technique is called gravity assist, or gravitational slingshot. And here's how it works. When a spacecraft approaches a planet, it falls into the planet's gravitational well, accelerating as it gets closer. If you time it right and approach at the correct angle, the spacecraft whips around the planet and gets flung out the other side, gaining speed from the planet's own orbital momentum. It's like a cosmic pickpocket. You steal velocity from a planet that's moving at tens of thousands of miles per hour around the sun, and the planet is so massive it doesn't even notice. Jupiter, for example, orbits the sun at about 29,000 miles per hour. If you can slingshot past it correctly, you can steal enough of that speed to reach Saturn without burning almost any fuel. But here's the genius part. Flandreau calculated that in 1977, Jupiter, Saturn, Uranus, and Neptune would be positioned like stepping stones across the solar system. A spacecraft launched at exactly the right time could visit Jupiter in 1979, use its gravity to reach Saturn in 1980, then Uranus in 1986, and finally Neptune in 1989. Without this alignment, visiting all 4 planets would require multiple spacecraft and decades of separate missions. With this alignment, it could be done in 12 years with 1 probe, 1 shot, 1 cosmic opportunity that wouldn't come again until the year 2053. Now, here's where most people misunderstand what happened next. They think NASA jumped on this opportunity immediately. They didn't. In 1965, when Flandreau made his discovery, NASA was drowning in other priorities. The Apollo program to land humans on the moon was consuming nearly every dollar and every engineer. President Kennedy had promised to land on the moon before the decade was out, and NASA was in an all-hands-on-deck race against the Soviet Union. Nobody wanted to hear about a mission to Neptune that wouldn't arrive until 1989. That's not 1989 like next year. That's 1989 like your children will be adults by then. Flandreau published his findings in a paper that should have set the space community on fire. Instead, it landed with a whisper. A few engineers took notice, started doing their own calculations, started dreaming. But dreams don't launch spacecraft. Money does. And in the mid-1960s, all the money was going to Apollo. So, Flandreau's grand tour, as it came to be called, sat on a shelf, waiting, while the planets slowly moved into position like the tumblers of a cosmic lock clicking into place. Then came 1969. Apollo 11. Neil Armstrong steps onto the moon. The space race, at least in the public's mind, was won. And here's the brutal reality of government funding. Once you win the race, people stop wanting to pay for it. NASA's budget was slashed, not trimmed, slashed. In 1965, NASA's budget was 4.4% of the entire federal budget. By 1970, it had dropped to less than 2%. Projects were canceled, engineers were laid off. The future of space exploration suddenly looked very uncertain. But a small group of scientists and engineers at JPL hadn't forgotten about the Grand Tour. Led by a man named Bruce Murray, who would later become the director of JPL, they started making noise. They wrote proposals. They gave presentations. They argued that this was a once-in-a-lifetime opportunity, literally once in 2 lifetimes. And if America didn't take it, no one would. Not just for this generation, but for the next 5 or 6 generations. Your great-great-great-grandchildren would grow up in a world where this chance had been missed. Congress wasn't impressed. In 1971, they looked at the proposed Grand Tour mission and saw the price tag, $750 million. In today's money, that's about $5.6 billion for a mission that would take 12 years to complete. That would visit planets nobody really cared about. Saturn, sure, it has rings, that's pretty. But Uranus, Neptune, who cares? They're just blurry dots in telescopes. Why spend $750 million to take pictures of blurry dots? The Grand Tour was dead, officially canceled by Congress in 1972. And this is where the story should end. This is where most impossible dreams die. Not with a bang, but with a budget committee meeting and a line item crossed out in red ink. But here's what happened instead. And this is the part that gives me chills every time I think about it. The engineers at JPL looked at the canceled Grand Tour and said, "Okay, you won't fund the full mission? Fine, we'll do it anyway. Just cheaper." They proposed a scaled-down version. Instead of 4 spacecraft visiting all 4 planets, they'd send 2 spacecraft to visit just Jupiter and Saturn. They wouldn't call it the Grand Tour. They'd call it Mariner Jupiter Saturn, making it sound like a simple extension of the successful Mariner missions that had already flown by Mars and Venus. The price tag? $250 million, 1/3 of the original cost. Congress said yes. But here's the secret that every engineer at JPL knew, but didn't say out loud. They were going to build these spacecraft to Grand Tour specs anyway. If Voyager 2 survived Jupiter and Saturn, if it still had enough power, if its instruments were still working, they could try for Uranus. And maybe, just maybe, if everything went perfectly, Neptune too. They were sneaking the Grand Tour through the back door, hiding it inside a more modest mission proposal. It was brilliant, it was borderline insubordinate, and it worked. Now, let me tell you about the political environment these engineers were working in, because it's crucial to understanding just how miraculous it was that Voyager launched at all. This is 1972, right? The Vietnam War is tearing America apart. Watergate is about to explode. The economy is struggling with oil shortages and inflation. And here's NASA asking for $250 million to take pictures of Saturn. The public sentiment was, we have problems here on Earth. Why are we wasting money in space? There's a famous story from this time. Bruce Murray was testifying before Congress, defending the Voyager budget. A senator looked at him and said, "Dr. Murray, we've been to the moon. We've won the space race. What's left to explore?" Murray's response has become legendary. He said, "Senator, imagine if Columbus had discovered the Bahamas and then Spain said, 'Well, we've seen islands. What else is there? We've touched the moon, but we haven't even sent a postcard from the outer solar system. We don't know what's out there. And if we don't go now, if we miss this planetary alignment, everyone in this room will be dead before it comes around again." That got their attention, but it wasn't enough. What finally saved Voyager was something more practical, more Cold War. Soviet probes had already visited Venus and Mars. The Soviets were planning missions to Jupiter. If America stepped back from planetary exploration, if we let this opportunity pass, the Soviets would own the outer solar system. And in the political calculus of the 1970s, that was unacceptable. Voyager wasn't just science, it was a flag-planting mission, a way of saying, we were here first. So the funding was approved, but with conditions. The mission would be exactly what was promised, Jupiter and Saturn only. Any attempt to go beyond that would require new approval, new funding, new political fights. The engineers smiled and nodded and went back to JPL to build spacecraft that could, theoretically, accidentally, maybe just happen to be capable of visiting Uranus and Neptune if things worked out. There's something deeply human about this story that I love. These weren't rule breakers or rebels. They were engineers and scientists who believed so strongly in what they were doing that they found a way to make it happen, despite the system working against them. They didn't lie. The spacecraft really could visit Jupiter and Saturn, and that's what they promised. They just built it better than required, more capable than necessary, with just enough resilience to maybe, possibly pull off the impossible if the universe smiled on them. But building a spacecraft that could survive the outer solar system, that could last not 5 years, but potentially 15 or 20, that could operate in conditions it was never officially designed for, that required engineering genius that bordered on magic. Every decision, every component, every line of code had to be chosen with an eye toward longevity that NASA had never attempted before. Because if Voyager was going to secretly continue to Uranus and Neptune, it had to be built like nothing else ever built. And that's exactly what they did. The story of how they engineered these two spacecraft, how they built machines that would outlive their creators and outperform every expectation, how they packed 1970s technology with capability that still impresses us today, that's where the real magic happened. Because Voyager isn't just about good luck or cosmic timing. It's about human ingenuity pushed to its absolute limit, about building something so well that it transcends its original purpose and becomes something greater. And the way they did it, the choices they made in the design and construction, those choices are still teaching us lessons about how to build things that last. Here's something that will blow your mind. The computer on Voyager 1, the one that's been navigating through interstellar space and managing all its systems for nearly half a century, has 69 kilobytes of memory. Not gigabytes, not megabytes, kilobytes. Your phone right now, sitting in your pocket, is literally 4 billion times more powerful. A modern pregnancy test has more computing power than Voyager. And yet, that pregnancy test will be in a landfill within a week, while Voyager is still exploring the cosmos 15 billion miles from home. So the question becomes, how did engineers in the 1970s, with technology that seems laughably primitive today, build something that would outlast and outperform almost everything we've created since? If you're ready to discover engineering decisions so brilliant they still make modern engineers jealous, and mistakes so catastrophic they almost killed the mission before it really began, stick around. Because what these engineers did with 1970s technology will make you rethink everything about how we build things today. Let's start with the most fundamental question. How do you power a spacecraft that's going to fly so far from the sun that solar panels become useless? Because here's the reality. At Jupiter's distance, sunlight is 25 times weaker than on Earth. By Saturn, it's 90 times weaker. At Neptune, 900 times weaker. Solar panels wouldn't just be inefficient, they'd be decorative. So the Voyager team needed a power source that would work in complete darkness in the cold of space for potentially decades. And they found it in one of the most controversial materials on Earth, plutonium-238. Now, before anyone panics, this isn't weapons-grade plutonium. This isn't plutonium that can be used in nuclear bombs. Plutonium-238 is a specific isotope that's incredibly rare and incredibly valuable because it does something almost magical. It generates heat naturally through radioactive decay, and that heat can be converted into electricity. The device that does this is called an RTG, radioisotope thermoelectric generator. Think of it as a nuclear battery, except instead of using chemical reactions like your phone battery, it uses the natural decay of radioactive atoms. Here's how it works. Plutonium-238 atoms are unstable. They're constantly falling apart, breaking down into other elements, and when they do, they release energy as heat. A lot of heat. The RTGs on Voyager started with about 470 watts of thermal power at launch. To put that in perspective, that's like having 4 or 5 old-fashioned incandescent light bulbs worth of heat. Doesn't sound like much, right? But here's the genius. Thermoelectric converters wrapped around this plutonium core convert that heat directly into electricity. No moving parts, no combustion, no solar panels that can break or get covered in dust. Just physics doing its thing, silently, reliably, for decades. When Voyager launched in 1977, its RTGs produced about 470 watts of electricity. Today in 2025, after 47 years of continuous decay, they're down to about 220 watts. That's a drop of more than half. And here's the brutal math that keeps the Voyager team up at night. Voyager needs about 200 watts minimum to keep functioning. They're now running on a margin so thin that every year they have to make gut-wrenching decisions about what to turn off. Last year they shut down one of the heaters protecting the cosmic ray instrument. The instrument is now operating at temperatures it was never designed to survive. But it's still working, because the engineers who built it in the 1970s didn't just meet the design specifications, they exceeded them by margins they never told anyone about. But power is only half the equation. You need a brain to control everything, and that brain had to be unlike any computer ever built. The main computer on Voyager, formerly called the Computer Command Subsystem, has 69.63 kilobytes of memory. Let me put that in perspective. The original Super Mario Bros. Game on Nintendo used 31 kilobytes. A single high-resolution photo from your phone is about 3 to 5 megabytes. That's 50 times more data than Voyager's entire memory can hold. And yet, this computer has been running continuously for 47 years, managing trajectory corrections, instrument operations, data collection, and transmission, all while dealing with cosmic radiation that should have fried its circuits decades ago. How is this possible? The answer is something called radiation hardening. Every single component in Voyager's computer was selected and tested for its ability to withstand radiation. They used older, simpler chips because newer, faster chips were more vulnerable to cosmic rays. They added redundancy at every level, triple redundant systems. If one circuit failed, 2 backups were ready. They used magnetic core memory for critical functions because unlike modern RAM, core memory doesn't lose data when hit by radiation. It's slower, it's bulkier, but it's nearly indestructible. And here's where it gets beautiful. The engineers knew that 69 kilobytes wasn't much even by 1977 standards. So they designed the software to be reprogrammable from Earth. Over the past 47 years, Voyager's software has been updated multiple times. They've uploaded new code to teach it how to operate with failing components, how to conserve power, how to point its antenna with thrusters that weren't designed for that purpose. They've essentially been performing brain surgery on a patient that's 15 billion miles away, and every operation has a 44-hour delay between cutting and seeing if it worked. But here's what really separates Voyager from every other spacecraft: the obsessive redundancy. The engineers didn't just build backup systems, they built backups for the backups, and then backups for those. Voyager has 2 computers, but within each computer are redundant circuits. It has 2 radio transmitters, but each transmitter can operate in different modes. It has 3 different types of thrusters for attitude control, because the engineers knew that different thrusters might fail in different ways. Every critical system has multiple failure modes accounted for. Now, let me tell you about a moment that almost destroyed everything, because it shows how even brilliant engineering can have blind spots. It's July 1979. Voyager 1 is approaching Jupiter, closing in for humanity's first close-up look at the giant planet and its moons. The camera platform, this is the part that holds the cameras and can rotate to point at different targets, starts acting strangely. It's moving, but not smoothly. It's jerking, stuttering, like it's fighting against something. Engineers send commands to stop it, reset it, try again. Nothing works. The platform is moving, but barely. And with each movement, it's getting worse. Imagine the panic. They're about to make history. They're about to see Jupiter's moons up close for the first time, and the camera platform, the entire reason for the mission, is failing. They run diagnostics, they analyze telemetry, and they discover the problem. Someone forgot to lubricate one of the gears properly before launch. Over the 2 years in space, with the temperature swings and the vacuum, the lubricant that was there had dried out. The gear was grinding metal on metal, wearing itself down with every movement. If they kept using it normally, it would seize up completely within days, maybe hours. So they made a brutal decision. They would move the camera platform as little as possible. Instead of smoothly tracking targets, they would point it, take pictures, then let it rest. They would limit movements to only the most critical moments, and most ingeniously, they would use the spacecraft's entire body as a camera platform when possible, rotating the whole spacecraft instead of just the camera mount. This saved the camera system, but it required rewriting the mission plan in real time, recalculating every photograph, every angle. And here's the kicker. This almost catastrophe taught them something crucial for Voyager 2. When Voyager 2's turn came to visit Jupiter 6 months later, they moved its camera platform very gently, very carefully, nursing it along. And it worked beautifully all the way through Neptune in 1989. That failure, that heart-stopping moment, when everything almost fell apart, made them better engineers and saved the Grand Tour. But let's talk about something most people never consider: temperature management. Space isn't just cold, it's variably cold. When you're near the sun, you're baking. When you're in shadow, you're freezing. And Voyager had to deal with both extremes. The electronics needed to stay warm enough to function, but not so hot they'd fry. The solution was elegant: layers of insulation, strategic heaters, and careful design of which components generated heat and where that heat needed to go. The most critical components sit in a 10-sided aluminum framework called the bus, wrapped in thermal blankets made of layers of aluminized mylar. These blankets reflect heat back inside when things get too cold and radiate excess heat when things get too warm. But as the RTG power decreased over the years, those heaters had to be turned off one by one. First, they shut off the heaters for non-critical components. Then they started shutting off heaters for scientific instruments, gambling that the instruments could survive colder temperatures than they were designed for. And astonishingly, most of them did. There's a philosophy embedded in every rivet and wire of Voyager that we've lost in modern engineering. It's called overbuilding, and it's generally considered wasteful today. Why make something last 50 years when it only needs to last 5? Why add redundancy when you can just replace it if it breaks? But the Voyager engineers couldn't replace anything. Every component had to be chosen with the assumption that it would face conditions worse than tested, would operate longer than specified, and would have no possibility of repair. So they tested everything beyond its ratings. If a component was rated for 10,000 cycles, they tested it for 50,000. If it was rated for temperatures down to 100 degrees, they tested it at 150 degrees. They used older, proven technology instead of cutting-edge components that hadn't been thoroughly tested. They chose simplicity over sophistication when reliability was on the line. And most importantly, they built in what engineers call graceful degradation, the ability for the spacecraft to lose functionality gradually rather than catastrophically. Think about your phone for a second. When your phone fails, it's usually total. The screen cracks and becomes unusable. The battery swells and it won't turn on. A water damage and it's dead. There's no halfway. But Voyager was designed so that as things failed, and they knew things would fail, The spacecraft could keep operating with reduced capability. Lose a transmitter? Switch to the backup. Lose a backup? Reduce data rate. Can't reduce data rate enough? Turn off non-essential instruments. Every failure point had a contingency, and every contingency had a contingency. There's a specific design choice I find fascinating. The antenna. Voyager's high-gain antenna is 3.7 meters across, shaped like a dish. It has to stay pointed at Earth with incredible precision, within a fraction of a degree, or we lose contact. In 1977, they installed a system that could track Earth automatically using sensors, but they also installed manual override systems, and they installed multiple types of thrusters that could rotate the spacecraft if the primary system failed, and they installed gyroscopes that could maintain orientation even if all else failed. They built 5 different ways to keep that antenna pointed at Earth, because they knew that if they lost pointing, they lost everything. Now, here's a comparison that should make every modern engineer uncomfortable. The total cost of the Voyager program, adjusted for inflation, was about $3.5 billion. That includes both spacecraft, the launch vehicles, the mission operations for decades, everything. Compare that to modern spacecraft. The James Webb Space Telescope costs $10 billion, and it's designed to last 10 years, maybe 20 if we're lucky. The Mars Curiosity rover costs $2.5 billion and has lasted 12 years. Those are incredible achievements, don't get me wrong, but Voyager achieved more, lasted longer, and cost less, even accounting for inflation. Why? Because the engineers who built Voyager were working in a different paradigm. They couldn't rely on rapid iteration and replacement. They couldn't plan for a repair mission. They had one shot to get it right, and they understood that right meant building something that would survive conditions they couldn't fully predict for durations they couldn't fully anticipate. That mindset, that commitment to resilience over efficiency, to longevity over cost cutting, created something that has outlived its creators and will outlive all of us. But engineering brilliance and political maneuvering only got Voyager to the launch pad. The real test came when these 2 identical spacecraft, built with such care and precision, actually encountered the giant planets they were designed to study. What they found at Jupiter, Saturn, Uranus, and Neptune didn't just expand our knowledge. It shattered our assumptions about how planetary systems work and revealed moons that might harbor life, worlds more alien and wonderful than science fiction had imagined. That journey, those discoveries, that's what transformed Voyager from a technical achievement into something transcendent. March 5th, 1979, 3 a.m. A geophysicist named Linda Morabito is sitting in a small room at JPL, staring at a photograph of Jupiter's moon, Io, that Voyager 1 had taken just hours before. She's not supposed to be looking at this image. She's supposed to be tracking navigation stars to help plot Voyager's trajectory. But something in this picture catches her eye. On the edge of Io, barely visible against the black of space, there's something that shouldn't be there. A plume. An umbrella-shaped cloud rising 190 miles above the surface. She stares at it for several minutes, checks other images, and then realizes what she's seeing. For the first time in human history, we're watching a volcanic eruption on another world. Active volcanism. On a moon that was supposed to be dead, frozen, geologically inactive. And this discovery, made almost by accident, would be the first of dozens of moments when Voyager shattered everything we thought we knew about the outer solar system. If you want to witness the greatest discoveries ever made in planetary science, discoveries that happened in real time as scientists watch their screens in disbelief, stay right here. Because what Voyager found at each planet didn't just surprise us, it fundamentally changed our understanding of where life might exist in the universe. Let's rewind to January 1979, 2 months before Linda Morabito's discovery. Voyager 1 is approaching Jupiter, and the excitement at JPL is electric. For months, the imaging team has been receiving pictures as Jupiter grows larger and larger in the frame. But these early images are disappointing. They're better than anything from Earth telescopes, sure, but they're still just pictures of Jupiter. The same bands, the same great red spot we've seen for centuries. Some scientists are starting to worry. Did we spend all this money just to take slightly better pictures of things we already knew about? Then Voyager gets close, really close, and everything changes. The first shock comes from Jupiter itself. The Great Red Spot, which we'd been observing since the 1600s, turns out to be a hurricane larger than Earth that's been raging for at least 350 years. But Voyager reveals it's not just a storm, it's a vertical structure extending 5 miles above the surrounding cloud deck, with winds at its edge reaching 270 miles per hour. Inside the spot, Voyager detects complex circulation patterns, smaller vortices within the larger storm, a weather system so massive and so stable that it makes Earth's most powerful hurricanes look like bathtub whirlpools. But Jupiter's atmosphere is just the opening act. The real drama is happening on the moons. Europa, one of Jupiter's 4 large Galilean moons, appears in the first close-up images as the smoothest object in the solar system. Not a single mountain, no craters to speak of, just a surface crisscrossed with dark lines that look like cracks in ice. The imaging scientists lean closer to their monitors. One of them says what everyone is thinking. That's not rock, that's ice. And something is breaking it, refreezing it, breaking it again. They've discovered an ocean world. Beneath Europa's frozen surface lies a liquid water ocean, kept warm by tidal heating from Jupiter's immense gravity. And where there's liquid water, there might be life. But here's what really gets me. They almost missed it. The mission plan had Voyager 1 focus primarily on Jupiter and Io. Europa was secondary, a backup target. If they hadn't taken those specific images at that specific angle, we might have waited decades to discover that Europa was an ocean world. One of the scientists later said, "We were looking for geology, and we found biology's best chance outside Earth." Now, about that volcanic discovery on Io. When Linda Morabito saw that first plume, she called her supervisor immediately. Within hours, the team was poring over every image of Io. They found eight active volcanic plumes erupting simultaneously. Not evidence of ancient volcanism, not dormant volcanoes, active eruptions happening right now. Io, it turns out, is the most volcanically active body in the entire solar system, with over 400 active volcanoes. The tidal forces from Jupiter literally knead Io like dough, generating so much internal heat that the entire moon is constantly melting and reforming. Its surface is younger than some buildings on Earth because it's completely resurfaced every few thousand years. Think about what this means. Before Voyager, we thought volcanic activity required a large planet with internal heat left over from its formation. Voyager proved that wrong. Tidal heating, gravitational squeezing, could keep a small moon volcanically active for billions of years. This discovery revolutionized our understanding of where we might find habitable environments in the universe. Suddenly, moons weren't just dead rocks orbiting planets. They were dynamic worlds with their own geologies, their own possibilities for life. And there's a discovery that still gives scientists chills. Jupiter has a ring. Nobody expected this. Saturn has rings. Everyone knows that. But Jupiter? When Voyager detected a faint ring around Jupiter, the team thought it was a data error. They checked and rechecked. But there it was. A thin, dark ring of dust and debris, completely invisible from Earth. If Voyager hadn't been positioned at exactly the right angle, looking back at Jupiter with the sun behind it, we never would have seen it. This accidental discovery taught us that ring systems might be common, not rare, and that we need to look at worlds from multiple angles to see their secrets. November 1980. Voyager 1 reaches Saturn, and if Jupiter was surprising, Saturn is mind-bending. We all know Saturn's rings, right? Those beautiful bands of ice and rock that make Saturn the jewel of the solar system. Before Voyager, we thought there were maybe 6 or 7 main rings with some gaps. Voyager 1 sends back images, and the scientists counting rings just stop. They can't keep up. Thousands of rings. Tens of thousands. The rings aren't solid bands. They're intricate structures, with gaps, waves, kinks, braids. Some rings have sharp edges, held in place by tiny shepherd moons that orbit alongside them, their gravity sculpting the ring particles into precise formations. One of the most bizarre discoveries, the F ring. This ring is braided, literally braided like hair, with multiple strands twisting around each other. The team saw the images and thought their instruments were malfunctioning. How could a ring braid itself? The answer: 2 small moons, Prometheus and Pandora, orbit on either side of the ring, their gravity pulling the ring particles into these impossible-looking braided structures. It's gravitational choreography on a scale that shouldn't exist. And yet, there it is, happening right in front of us. But Saturn's biggest surprise isn't the rings, it's Titan. Saturn's largest moon, Titan, is bigger than the planet Mercury. Before Voyager, we knew Titan had an atmosphere, but we thought it was thin, insubstantial. Voyager 1 approaches Titan and discovers something that stops everyone cold. Titan's atmosphere is thicker than Earth's. At the surface, the atmospheric pressure is 1.5 times Earth's sea level pressure. And it's not just thick, it's opaque. The entire moon is wrapped in an orange-brown haze of complex organic molecules. Voyager's cameras can't see through it. The surface is completely hidden. But Voyager's other instruments can penetrate the haze. They detect nitrogen, methane, ethane, and dozens of complex hydrocarbons. The atmosphere is a chemical factory, constantly creating organic molecules. Scientists realize they're looking at a moon that might resemble early Earth, a place where the chemistry of life might be happening right now in ways we don't understand. The lead scientist on the imaging team said something I'll never forget. We went to Saturn to see rings, and instead we found a second chance to understand how life begins. August 1986. Voyager 2 reaches Uranus, and immediately nothing makes sense. Every other planet in the solar system spins upright, give or take a few degrees of tilt. Uranus is lying on its side, tilted 98 degrees. It's essentially rolling around the sun like a barrel instead of spinning like a top. Something? Probably a massive collision with an Earth-sized object billions of years ago, knocked Uranus sideways. And because of this tilt, Uranus has the most extreme seasons in the solar system. Each pole faces the sun for 42 years straight, then faces away into darkness for 42 years. Imagine 42 years of continuous daylight, followed by 42 years of continuous night. But the real mystery of Uranus is its magnetic field. Every other planet with a magnetic field has it roughly aligned with its rotation axis. Earth's magnetic poles are close to our geographic poles. Jupiter's, same thing. Uranus? Its magnetic field is tilted 59 degrees from its rotation axis and offset from the center of the planet. When Voyager measured this, scientists thought the instruments had failed. They recalibrated everything. The readings were correct. Uranus's magnetic field is just wrong. To this day, we don't fully understand why. It's like the planet is breaking the rules of planetary physics and no one told it that's not allowed. The moons of Uranus are equally bizarre. Miranda, the smallest of the 5 large moons, looks like it was smashed apart and reassembled incorrectly. Its surface has massive cliffs, some over 12 miles high. That's more than twice the height of Mount Everest. There are regions with completely different terrain types butted up against each other, like someone cut up different moons and glued the pieces together randomly. The most accepted theory is that Miranda was shattered by a massive impact, and gravity slowly pulled the pieces back together. But they didn't fall back into their original positions. It's a jigsaw puzzle moon, and it's absolutely haunting to look at. August 1989, Voyager 2 arrives at Neptune, the final stop of the Grand Tour. And Neptune, it turns out, is the most active, most violent planet in the outer solar system, despite being the coldest. With surface temperatures of 353 degrees, Neptune should be calm, dead, frozen. Instead, Voyager finds winds moving at 1,200 miles per hour, the fastest winds ever measured in the solar system. These are supersonic winds, faster than the speed of sound in Neptune's atmosphere. No one understands where the energy is coming from. Neptune receives 900 times less sunlight than Earth. By all logic, it should be a frozen, quiet ball. Instead, it's raging. The Great Dark Spot on Neptune mirrors Jupiter's Great Red Spot, a massive storm system the size of Earth. But unlike Jupiter's spot, which has been stable for centuries, Neptune's dark spots appear and disappear within years. Voyager saw one in 1989. By 1994, when Hubble looked back, it was gone. Neptune is changing, evolving, churning with an energy source scientists still debate about. But Neptune's moon Triton, that's where things get truly alien. Triton is the only large moon in the solar system that orbits backward, retrograde, against the direction Neptune rotates. This tells us that Triton didn't form with Neptune. It was captured, probably from the Kuiper Belt. And despite being one of the coldest places in the solar system, at 301 degrees, Triton is geologically active. Voyager photographed ice volcanoes, cryovolcanoes, erupting plumes of nitrogen gas and ice particles 5 miles into space. On one of the coldest worlds we've ever seen, there are geysers, active geology in a frozen wasteland. It's like finding a furnace in Antarctica. Here's what strikes me most about this entire grand tour. At every single planet, Voyager found things we didn't predict, couldn't have predicted, because our imaginations were too limited. We thought we understood how planetary systems work, and Voyager showed us we understood almost nothing. Active volcanoes on tiny moons, ocean worlds beneath ice, braided rings, planets lying on their sides, storms that last for centuries, moons captured from other parts of the solar system. Every encounter rewrote the textbooks. And here's a question worth pondering. What did we miss? Voyager flew past these worlds in a matter of hours or days. It saw one hemisphere of each moon, one moment in their multi-billion-year histories. Imagine if an alien spacecraft flew past Earth for just a few hours. It might miss hurricanes, miss volcanoes, miss the northern lights, miss entire continents if it happened to fly past the wrong side. What are we missing about these worlds because we only got one quick look? The scientists who worked on Voyager talk about a feeling that haunts them, watching their life's work flash past in hours, knowing they will never get another chance to look. Bradford Smith, leader of the imaging team, said after the Neptune encounter, "We spent 12 years preparing for 48 hours of observation, and now it's over. We've seen these worlds once, and we'll never see them this way again in our lifetimes." That mixture of triumph and grief, of discovery and loss, it's captured in every photograph Voyager sent back. But Voyager carried something else on its journey, something that had nothing to do with science and everything to do with hope. Before it launched, a team led by Carl Sagan assembled a message, a gift, a greeting to whoever might someday find these lonely spacecraft drifting through the galaxy. They created a golden record containing the sounds and images of Earth, a time capsule of humanity frozen in 1977, and the story of what they chose to include, what they left out, and what it means to send a message that might not be received for millions of years. That's a story about who we are and who we hope to become. February 1977, 5 months before Voyager's launch. Carl Sagan sits in a conference room at Cornell University with a small team of scientists, artists, and writers, staring at a problem that seems impossible. NASA has given them permission to attach a message to Voyager, a greeting to any alien civilization that might someday encounter these spacecraft drifting through the galaxy. They have one golden record, 12 inches in diameter, that can hold 90 minutes of audio and 115 images. And they have 6 weeks to decide. Out of everything humanity has ever created, everything we've ever said, sung, photographed, or dreamed, what do you choose? How do you summarize an entire planet, an entire species, in 90 minutes? And here's the truly terrifying part. Whatever they choose will be humanity's voice in the universe long after we're gone. The pressure of that choice, Sagan would later say, was suffocating. If you want to know what we said to the cosmos, what we chose to represent humanity, when we had just one chance to introduce ourselves to the universe, and why some of those choices are deeply controversial even today, this is a story you need to hear. Hit that like button if you're curious about what message we sent to the stars. Let me take you inside the room where these decisions were made, because the process was far more chaotic and emotional than most people realize. The team had assembled in January 1977. 6 weeks. That's all they had. 6 weeks to create something that needed to last for billions of years and speak for an entire species. Carl Sagan was the public face, the name everyone knows, but the real work was done by a small group. Frank Drake, the astronomer who created the famous Drake equation for calculating alien civilizations. Linda Salzman Sagan, Carl's wife, an artist who would create the cover diagrams. Anne Druyan, a writer who would become the creative heart of the project. Timothy Ferris, a music critic and producer. And John Lomberg, an artist who specialized in space art. The first question they had to answer: who are we making this for? And here's where it gets philosophically fascinating. They knew the odds of any alien civilization ever finding Voyager were essentially zero. Voyager 1, traveling at 38,000 miles per hour, will take 40,000 years just to reach the distance of the nearest star. The galaxy is incomprehensibly vast. The chances of Voyager coming anywhere near another star system with intelligent life are so small that they might as well be impossible. So, why make the record at all? Anne Druyan, in an interview years later, explained it this way: "We weren't really making this for aliens. We were making it for us. It was an exercise in figuring out who we are, what we value, what we want to say about ourselves. It was a portrait of Earth, painted at a specific moment in history, 1977, and it reveals as much about what we chose to leave out as what we chose to include. And what they left out is revealing. The team debated for hours about whether to include any images of war, violence, poverty, or suffering. Some argued that showing only Earth's beauty and achievements would be dishonest, a sanitized version of humanity that ignored our capacity for cruelty. Others argued that we should present our best selves, our aspirations rather than our failures. In the end, they made a choice that still bothers some people. The golden record shows almost no human conflict, no wars, no weapons, no poverty, no disease. It's an optimistic portrait, maybe unrealistically so, of what we want to be rather than what we are. Now let's talk about the music, because this is where things got really contentious. 90 minutes of audio. What music represents all of humanity? They knew they needed diversity, not just Western classical music, but sounds from every continent, every culture. But here's the problem. In 1977, getting permission to use copyrighted music was complicated and expensive. They had almost no budget. And the record companies, when they heard that this music would be sent into space, potentially forever, started demanding absurd licensing fees. The team sent a request to Chuck Berry's representatives asking to include Johnny B. Good. The response came back $50,000 for one song for a non-profit scientific mission. NASA's entire budget for the golden record was less than $25,000. They were prepared to give up when Chuck Berry himself heard about the project and personally intervened, waiving the fee. He said something beautiful. "If aliens want to hear my music, they can have it for free." But the Beatles weren't so generous. The team desperately wanted to include "Here Comes the Sun." It felt perfect, hopeful, universal, joyful. They approached EMI Records, the Beatles label. EMI refused. They demanded a fee that NASA couldn't pay, and they wouldn't budge. To this day, there's no Beatles music on the golden record, even though many people involved consider it one of their biggest regrets. Imagine, we sent Beethoven, we sent Bach, we sent Chuck Berry, but the most influential band in modern music is absent because of copyright disputes. What they did include is fascinating. Beethoven's Fifth Symphony and Cavatina from his String Quartet No. 13, Bach's Brandenburg Concerto No. 2, and Gavotte en Rondeau from the Partita No. 3 for solo violin, Mozart, Stravinsky. That's the Western classical tradition. But they also included a Navajo night chant, a Peruvian wedding song, a Pygmy girl's initiation song from Zaire, a Japanese shakuhachi piece, Indian raga, Azerbaijani bagpipes, Bulgarian folk music, and Aboriginal songs from Australia. They were trying, within their limited space and time, to show that humanity isn't one culture. We're thousands of cultures, each with their own music, their own beauty. And then there's Dark Was the Night, Cold Was the Ground by Blind Willie Johnson. This one gets me every time. It's a gospel blues song from 1927, recorded by a Blind Street musician in Dallas, Texas. There are no words, just Willie Johnson humming and moaning while playing slide guitar. Why include this? Because Timothy Ferris, the music producer, argued that it was the most emotionally pure piece of music he'd ever heard. It's a song about loneliness, about suffering, about reaching out for comfort in the darkness. And now it's traveling through the literal darkness of space, further from home than any human artifact. There's something profoundly moving about that. The images were equally debated, 115 photographs to represent Earth. They included the DNA structure, mathematical definitions, the solar system, continental drift, photos of Earth from space, but also a nursing mother, a family group, children, people eating and drinking, scientific diagrams next to deeply human moments. The team understood that if aliens ever found this record, they would need context, not just to understand what humans are, but to understand what life itself is. One image sparked massive controversy. The anatomically correct drawings of a man and a woman, naked, showing human reproduction. NASA nearly rejected it. Some officials argued it was obscene, that it would offend people. Linda Salzman Sagan, who drew the figures, had to fight to keep them on the record. Her argument was simple. If we can't show aliens what we look like, what we actually are, then what's the point? The drawings stayed, but as a compromise, they're less detailed than originally planned. Even on a message to aliens, we couldn't escape our own prudishness. Now here's something that very few people know about. Anne Druyan, who was developing the concept for the record with Carl Sagan, came up with an idea that was either brilliant or insane, depending on who you ask. She suggested recording a human's brainwaves and including them on the record, not thoughts translated into words, but the actual electrical patterns of a brain, thinking, feeling, experiencing consciousness. The idea was that an advanced civilization might be able to decode these patterns, might be able to literally read the thoughts and emotions of the person being recorded. They chose Anne Druyan herself as the subject. On June 3, 1977, she went to Bellevue Hospital in New York, where they attached electrodes to her head to record an EEG. She was told to think about specific things, the history of Earth, human civilizations, the problems we face, her hopes for the future. But something else was happening that day, something she couldn't control. Carl Sagan had just proposed to her the night before. She was in love, intensely, overwhelmingly in love. And as she sat there with electrodes attached to her head, supposedly thinking about Earth's history, part of her brain was just thinking about Carl, about their future together, about the feeling of falling in love. So here's what's actually on the golden record. Encoded in a section labeled brainwaves is the electrical signature of a woman falling in love. Not intentionally, not as part of the official content, but it's there, mixed in with everything else. Anne Druyan later said, "My feelings about Carl are eternally preserved on that record. Anyone who decodes it will be experiencing my feelings at one of the happiest moments of my life." Imagine that. A love story, encrypted in electrical impulses, traveling through the cosmos. But the most haunting part of the golden record isn't what's on it. It's the spoken greetings. They recorded greetings in 55 languages, from ancient Sumerian to Cantonese to Welsh. Each greeting is different, but they all say essentially the same thing. Hello, we are here, we come in peace. We want to be friends. The greetings are optimistic, friendly, sometimes touchingly simple. The one in English, spoken by Carl Sagan's 6-year-old son, Nick, just says, "Hello," from the children of planet Earth. That greeting is currently 15 billion miles from Earth, moving through interstellar space, and it will keep moving for millions of years. That child's voice frozen in time, long after everyone who knew him is gone. Here's what keeps me up at night about the golden record. Let's say, against all odds, an alien civilization finds it, maybe in 40,000 years when Voyager passes near another star. Maybe in 40 million years. What will they learn about us? They'll hear music that no longer exists. They'll see images of a planet that has changed beyond recognition. They'll hear greetings in languages that are dead. Everything on that record is a time capsule from 1977. And 1977 is already ancient history. The world it depicts, before personal computers, before the internet, before climate change became undeniable, before so many of the crises we face now, that world is gone. The golden record is a message from the dead to the future. Everyone who created it is either elderly now or has passed away. The Earth it shows is a memory, and yet it's still out there, still perfect, still golden, carrying our voices into forever. Frank Drake, one of the creators, was once asked, "Do you really think aliens will ever find it?" He answered, "Probably not. The record will survive for 1 billion years, maybe longer. But the odds of it being found are infinitesimal. It's more likely that the last surviving trace of humanity will be that record floating through space long after Earth is gone, long after the sun has burned out." Pause on that for a second. The golden record might be the last evidence that we ever existed. Not our cities, not our books, not our greatest achievements. Just a gold-plated record with 90 minutes of music and 115 pictures drifting in the void. So, what does it mean to send a message you know will probably never be received? Carl Sagan answered this best. He said, "The launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. It says that despite our differences, our wars, our problems, we can do something grand and beautiful. We can speak with one voice. We can say to the universe, here we are. This is what we were, and we reached out because we had to." Think about what was happening on Earth in 1977. The Vietnam War had just ended. The Cold War was raging. Dictatorships ruled much of the world. There were famines, wars, injustices everywhere. And yet, a group of people took time to create something beautiful, something hopeful, something that looked beyond our immediate problems and said, "We matter. What we create matters, and we want someone, somewhere, to know we were here." But there's a darker reading of the golden record that we should acknowledge. Some critics argue that it's almost imperialistic in its assumptions. We sent out this record assuming that any alien civilization would want to hear from us, would understand us, would care. We assumed they'd have ears to hear music, eyes to see images, minds that think like ours. We assume they'd be friendly, curious, benign. What if we're wrong? What if the golden record is a beacon leading something dangerous to Earth? Carl Sagan dismissed these concerns, but they're worth considering. By announcing our presence to the universe, did we do something brave or something reckless? There's one more thing on the golden record that I find unbearably beautiful. In addition to all the music and images and greetings, they included printed diagrams on the cover explaining how to play the record. They used the wavelength of hydrogen atoms as a universal measurement, assuming any advanced civilization would understand basic physics. They drew diagrams showing how to convert the electrical signals into images and sound. They even included a stylus made of ultra-pure uranium-238, which can be used as a radiometric clock. By measuring how much of the uranium has decayed, aliens could calculate exactly how long ago the record was made. So, even if humanity is gone, even if Earth is destroyed, even if the sun has exploded into a red giant, an alien finding this record could measure the decay of that uranium stylus and know this was made by a civilization that lived approximately X billion years ago. We built a timestamp into our message, a way of saying, this is when we lived, this is when we mattered. But all of this, the golden record, the music, the images, the messages, was secondary to Voyager's real mission. The science, the discoveries. Because while the golden record was a message to the future, Voyager's observations were rewriting our understanding of the present. The data it sent back, the images of volcanoes and rings and frozen oceans, didn't just answer questions, they changed what questions we knew to ask. And some of those discoveries, particularly one photograph taken as Voyager was leaving the solar system, would shift humanity's perspective on our place in the universe in a way that no other single image ever has. February 14th, 1990, Valentine's Day. Voyager 1 is 3.7 billion miles from Earth, already past Neptune, already beyond the edge of the planetary system. Its cameras have been shut off for years to conserve power. The mission is essentially over. All the planets have been visited, all the planned photographs taken. But Carl Sagan won't let it go. He's been lobbying NASA for months, begging them to do something that seems pointless, maybe even wasteful. He wants Voyager to turn around, one last time, and take a picture of Earth. Not because we need another picture of our planet, we have thousands, but because no human-made camera has ever photographed Earth from that far away. And what NASA doesn't know yet is that this one photograph, this seemingly unnecessary final snapshot, will become the most important image in the history of space exploration. Not for what it shows scientifically, but for what it makes us feel. If you want to understand how a single pixel in a photograph changed humanity's perspective on everything, our conflicts, our importance, our place in the cosmos, and why the discoveries Voyager made go far beyond planetary science into something more profound, stay with me. This might be the most important story I tell you all night. And if it moves you the way it moves me, show some love with that like button. Let me take you inside the debate that almost prevented this photograph from happening, because it reveals something crucial about the difference between what science measures and what science means. Carl Sagan was persistent, almost annoying about it. He kept bringing it up in meetings, kept writing memos, kept calling people at NASA. His argument was simple. We've spent billions of dollars sending these spacecraft to the outer planets. Before we shut the cameras off forever, let's take one family portrait. Let's photograph the solar system from the outside looking in. Let's see ourselves the way no one has ever seen us. NASA's response was equally simple. Why? What scientific value does this have? The cameras are old. We're not sure they still work properly. The spacecraft's power is limited. Turning it around, pointing the cameras back at the inner solar system, that takes energy we might need for other instruments. And what will we learn? We know what Earth looks like. We know what the planets look like. This is nostalgia, not science. But Sagan was arguing for something that can't be measured in data points. He was arguing for perspective, for humility, for a way of seeing ourselves that might change how we think about our problems, our wars, our divisions. He managed to convince enough people at NASA, barely, to approve the maneuver. On Valentine's Day 1990, Voyager 1 turned its cameras toward the inner solar system and began taking a series of photographs. 60 frames total, a mosaic of the solar system from 3.7 billion miles away. And then the images came down. Venus, bright and clear. Jupiter, visible but distant. Earth was in one of the frames, but when scientists first looked at the image, they couldn't find it. They searched the photograph, pixel by pixel, looking for our planet. And then someone spotted it. A pale blue dot, barely visible, suspended in a shaft of scattered sunlight. Less than 1 pixel in size. That's Earth. That's home. That's everything and everyone you've ever known, reduced to 0.12 pixels in a photograph. Carl Sagan later wrote about this image in a way that still gives me chills. He said, "Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." Think about what he's saying. Every war in human history fought over that pale blue dot. Every empire rising and falling on that speck. Every achievement, every tragedy, every moment of joy or despair, happening on something so small, it's barely visible from the edge of our own solar system. Not from another galaxy, from just past Neptune, still within our cosmic neighborhood, and already we're invisible. The pale blue dot photograph did something that no scientific discovery could do. It made our conflicts seem absurd. All the things we fight about, borders, resources, ideologies, they're happening on a pixel, a fraction of a pixel. Imagine explaining to someone from another world why humans kill each other over invisible lines drawn on this tiny dot, or over which interpretation of which ancient text is correct, or over who should control which microscopic portion of this speck. From Voyager's perspective, it all seems insane. But here's what really gets me. That photograph almost didn't happen for another reason. When they were processing the images, some of them showed unusual streaks of light, scattered sunlight that made the photographs look contaminated, like there was a problem with the camera. NASA almost discarded those images as corrupted data. Earth happened to be sitting right in one of those sunbeams, making it even harder to see. If the engineers had decided that streak of light was a camera malfunction and deleted those frames, we would have lost the pale blue dot forever. It survived by accident, by someone deciding to look closer instead of assuming it was junk data. Now, while the pale blue dot is the most famous image, there are discoveries from Voyager that have had equally profound impacts on science, even if they're less known to the public. Let me tell you about the bow shock. Before Voyager, we thought we understood the heliosphere, the bubble of solar wind that surrounds our solar system. We assumed it was relatively smooth, relatively stable, with a clear boundary where the solar wind meets the interstellar medium. Voyager proved us wrong. As Voyager 1 approached the edge of the solar system, its instruments detected something unexpected. The boundary isn't a line, it's a region. A turbulent, dynamic region where the solar wind slows down, compresses, and eventually stops. This region is called the termination shock, and Voyager 1 crossed it in December 2004. The instruments detected a sudden drop in solar wind speed from 250 miles per second to almost zero. It was like driving on a highway and suddenly hitting a wall of traffic that forces you to slam on the brakes. But here's what shocked everyone. The boundary kept moving. When Voyager 2 crossed the termination shock 3 years later, it wasn't in the same place. The heliosphere, this massive bubble that we thought was static, is actually breathing. It expands and contracts with the solar cycle, with changes in the sun's magnetic field, with the pressure of the interstellar medium pushing back against it. We discovered that our solar system has weather, not just planetary weather, but heliosphere weather. The entire solar system is a dynamic, living system in ways we never imagined. And this discovery has practical implications. The heliosphere protects Earth from galactic cosmic rays, high-energy particles from deep space that are dangerous to life. Understanding how the heliosphere fluctuates helps us predict periods when Earth might be more exposed to this radiation. For astronauts traveling to Mars or beyond, this information could be life or death. Voyager isn't just exploring space, it's teaching us how to survive in it. Then there's the discovery of the hydrogen wall. In 1992, Voyager's instruments detected something bizarre, a wall of hydrogen atoms piling up just beyond the heliopause. Think of it like snow piling up against a fence in a windstorm. The interstellar medium, the gas and dust between stars, is running into our solar system's magnetic field and accumulating. This hydrogen wall marks the true edge of the sun's influence, and we had no idea it existed until Voyager detected it. Here's why this matters. Every star has a heliosphere. Every star pushes back against the interstellar medium, which means the entire galaxy is filled with these bubbles, these protective shells around stars, all of them jostling against each other, creating boundaries and walls and turbulent regions we can't see from Earth. Voyager gave us our first glimpse of what interstellar space actually looks like. And it's not the empty void we imagined. It's structured, dynamic, filled with invisible architecture. But perhaps the most philosophically important discovery from Voyager is what it tells us about the rarity, or commonality, of life. The mission to Europa, the discovery of a subsurface ocean, changed the equation for where we should look for life in the universe. Before Voyager, we assumed life needed 3 things: liquid water, energy from a star, and a rocky planet in the habitable zone. Voyager showed us we were wrong on all counts. Europa has liquid water not because it's in the habitable zone. It's way too far from the sun for that. But because Jupiter's gravity literally kneads it like dough, generating heat through tidal forces. This means moons, not just planets, can harbor oceans. And if moons can have oceans, then the number of potentially habitable worlds in the universe just exploded. Our galaxy alone has hundreds of billions of planets, and many of those planets have moons. How many ocean worlds are out there? Dozens in our solar system alone, hundreds of billions in the galaxy. And we didn't know to look for them until Voyager accidentally photographed volcanoes on Io and cracks in Europa's ice. Here's a thought experiment that Carl Sagan posed. What if life is common in the universe, but it's mostly subsurface? What if most living things in the galaxy exist in dark oceans beneath ice, heated by tidal forces, never seeing stars, never developing technology, never sending signals into space? We've been listening for radio signals from alien civilizations for decades. But what if most life in the universe is like the creatures in Europa's ocean might be? Blind, aquatic, never wondering what's beyond their ice ceiling because they don't even know there is a beyond. Voyager data is still being analyzed today, and we're still finding new discoveries. In 2012, when Voyager 1 crossed into interstellar space, its instruments detected something that fundamentally changed our understanding of cosmic rays. Scientists had assumed that most cosmic rays came from distant supernova explosions. But Voyager's data showed that at the boundary between the heliosphere and interstellar space, cosmic rays actually increased dramatically. This suggests that the sun itself, or the interaction between the solar wind and interstellar medium might be creating cosmic rays. We're still trying to understand what this means. And there's this haunting discovery from 2018. Voyager 2, which had crossed into interstellar space in November 2018, detected that the interstellar magnetic field is stronger than predicted and points in a different direction than models suggested. This might seem like a minor detail, but it means our models of how the galaxy's magnetic field is structured are wrong. We thought we understood the Milky Way's magnetic architecture. Voyager is telling us we don't. Think about what this means. We've sent exactly 2 objects into interstellar space, Voyager 1 and Voyager 2. That's it. 2 data points. And already those 2 data points are forcing us to rewrite textbooks about the galaxy we've lived in for hundreds of thousands of years. How much more don't we know? How many of our assumptions about the universe are based on seeing things from only one perspective, from inside the solar system, looking out? There's a specific data set from Voyager that keeps scientists up at night. The plasma wave instrument has been detecting what they call plasma oscillations, ripples in the charged particles of interstellar space. These oscillations suggest that Voyager is passing through regions of varying density in the interstellar medium. Sometimes the space between stars is denser, sometimes it's thinner. We have no idea why. We don't know what creates these variations. And we can't study them from Earth because our instruments aren't sensitive enough to detect such subtle changes. So, here's the reality. Voyager is humanity's only sensor in interstellar space. When these spacecraft finally go silent, we'll be blind again. We'll go back to making assumptions about what interstellar space is like based on models and theories, without any direct measurements. It's like having one thermometer that works outside your house, and knowing that when it breaks, you'll have to guess the temperature forever after. But beyond all the technical discoveries, beyond the data and the measurements and the science, Voyager gave us something more valuable, a new story about who we are. Before Voyager, our story was Earth-centric. We were the center of creation, or at least the center of our own attention. The pale blue dot changed that narrative. It showed us, viscerally, that we're not the center of anything. We're inhabitants of a tiny world, one of 8 planets around an average star, in an unremarkable region of a galaxy containing hundreds of billions of stars. This should be depressing, right? We're insignificant, meaningless, cosmically irrelevant. But somehow, for many people, the pale blue dot has the opposite effect. It's liberating. If we're this small, then our conflicts are even smaller. Our hatreds, our divisions, our wars over resources and ideologies, they're happening on a scale so minute that the universe doesn't even notice. From Voyager's perspective, there are no nations, no borders, no us and them. There's just us, just humanity, just life, clinging to a rock in the void. Carl Sagan concluded his reflection on the pale blue dot with this: "There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another, and to preserve and cherish the pale blue dot, the only home we've ever known. Has it worked? Has the pale blue dot made us kinder, more responsible, more unified? I'd argue yes and no. Yes, because it's changed how millions of people see the Earth, not as a collection of separate nations, but as one fragile ecosystem, one shared home. The environmental movement, the push for global cooperation on climate change, the growing sense that we're all in this together. These ideas are easier to embrace when you've seen that photograph. But no, because we're still fighting wars, still destroying the environment, still treating Earth like it's infinite when we can see that it's just a dot. The pale blue dot gave us perspective, but perspective alone doesn't change behavior. Knowledge doesn't automatically lead to wisdom. Still, I find hope in the fact that the image exists, that it's out there, in textbooks and museums and websites, reminding anyone who looks at it that their problems, however overwhelming, are taking place on a stage almost too small to see. It's a tool for humility, and humanity desperately needs humility. What would it take for that perspective to actually change how we live? That's the question I keep coming back to. Because Voyager didn't just give us data, it gave us a mirror, and what we see in that mirror, whether we like it or not, is the truth about our place in the universe. We're small. We're vulnerable. We're alone on this pale blue dot, at least as far as we know. And if we destroy it, if we make it uninhabitable through war or pollution or neglect, there's nowhere else to go. Not yet, maybe not ever. But recognizing our vulnerability, our cosmic insignificance, doesn't mean we should give up or despair. It means the opposite. It means that what we do here, on this tiny world, matters more than ever. Because this dot is all we have, and somehow, against impossible odds, this dot produced life, consciousness, art, music, love, curiosity, all the things that make existence worth existing. That's not insignificant, that's miraculous. And miracles, especially ones happening on such a small stage, deserve to be protected. Yet for all these discoveries, for all the data Voyager has sent back, the real miracle isn't what it found, it's that it's still working at all. Because keeping Voyager alive has required a level of creativity, problem solving, and sheer determination that borders on the heroic. Every year brings new crises, new failures, new impossible decisions about what to sacrifice to keep the mission going just a little bit longer. The story of Voyager's survival is a story of human ingenuity fighting against entropy, against the inevitable decay of all things, knowing that we'll lose eventually, but refusing to surrender 1 second sooner than we have to. November 14th, 2023. Engineers at NASA's Jet Propulsion Laboratory stare at their computer screens in disbelief. Voyager 1, humanity's most distant spacecraft, 15 billion miles from Earth, has started speaking gibberish. Instead of coherent data packages, it's sending back a repeating pattern of ones and zeros that makes no sense. It's like calling your elderly parent and hearing them speak in word salad, and you know something is terribly, terribly wrong. The team runs diagnostics. They send commands. Nothing changes. Voyager 1's brain, one of its 3 computers, has suffered what appears to be a corrupted memory chip. After 46 years of flawless operation, one tiny piece of hardware has failed. And here's the nightmare. They have no way to repair it. They can't send a technician. They can't reboot it remotely without risking total failure. They have to perform brain surgery on a patient that's 15 billion miles away, using commands that take 45 hours to send and receive a response. And if they make one wrong move, Voyager 1 goes silent forever. If you want to witness the most nail-biting troubleshooting sessions in the history of space exploration, where engineers are literally inventing solutions on the fly to problems no one has ever faced before, stay with me. Because keeping Voyager alive isn't about good engineering anymore. It's about miracles. And if this story of human determination against impossible odds resonates with you, help us reach more people by hitting that like button. Let me take you inside that crisis room in November 2023, because what happened over the next 5 months is almost unbelievable. The problem was in the flight data system, one of Voyager's 3 computers. This computer is responsible for packaging science data before it's transmitted to Earth. When it started malfunctioning, Voyager could still receive commands, could still function, but it couldn't tell us what it was seeing. It was like having eyes but no mouth. The team knew that somewhere in the 69 kilobytes of memory, a single chip had failed. Think about that. 69 kilobytes. Your email signature probably has more data than that. And they had to locate which specific section of memory was corrupted. Without being able to directly examine the hardware, they started sending diagnostic commands, waiting 22.5 hours for each response, analyzing the garbled data for patterns. It was detective work at light speed delays. December 2023 came and went. Voyager 1 was still speaking nonsense. January 2024, still gibberish. The team tried something desperate. They commanded Voyager to send them a full memory dump, a complete readout of everything stored in the flight data system. The data came back, and engineers spent weeks analyzing it line by line. And finally, in March 2024, they found it. A single chip containing about 3% of the flight data system's memory was dead. 3% doesn't sound like much, but that chip contained critical code that the system needed to function. Here's where it gets brilliant. They couldn't repair the chip, but they could work around it. The team realized that if they could relocate the code from the dead chip to other parts of memory, splitting it up among multiple locations, they might be able to restore functionality. But there was a problem. Those other memory locations weren't empty. They contained other code, other critical functions. They would have to carefully move things around, like solving a Rubik's Cube, where one wrong move crashes the entire system. On April 18, 2024, they sent the new code to Voyager 1. 22.5 hours later, they held their breath and waited for a response. And then, after 5 months of gibberish, Voyager 1 started sending coherent data again. The team had successfully performed remote brain surgery on a 46-year-old computer, 15 billion miles away. One engineer said it was like fixing a 1977 Volkswagen Beetle's engine while it's driving down the highway at 38,000 miles per hour. And you're standing in New York giving instructions to someone in Tokyo who's giving instructions to someone in Australia who's actually turning the wrenches. And you can't see what you're doing. And each instruction takes 2 days to execute. But this wasn't the first crisis. Not even close. Let me tell you about the thruster problem from 2017 because it perfectly illustrates the philosophy of the Voyager team. When something breaks, get creative. Voyager 1 uses small thrusters to keep its antenna pointed at Earth. Think of them like tiny steering jets that fire in short pulses to adjust the spacecraft's orientation. The primary thrusters, the ones used since launch, started showing signs of degradation in 2014. They were clogging up, requiring longer pulses to achieve the same correction. By 2017, the team realized they had maybe months before these thrusters would fail completely. But here's the thing. Voyager has backup thrusters, trajectory correction maneuver thrusters, designed for course adjustments during the planetary flybys. They hadn't been fired since November 8, 1980, 37 years earlier during the Saturn encounter. Nobody knew if they would still work. The fuel in them might have degraded. The fuel lines might be clogged. The valves might be frozen. The team made a decision. On November 28, 2017, they sent commands to fire these backup thrusters. The signal took 19 hours and 35 minutes to reach Voyager 1. Then they waited another 19 hours and 35 minutes for the response. Imagine that tension. If the thrusters didn't fire, if they misfired, if anything went wrong, Voyager 1 would lose its orientation. The antenna would drift away from Earth. They'd lose contact, possibly forever. The response came back. The backup thrusters fired perfectly. Thrusters that had been dormant for 37 years woke up and worked like they'd been used yesterday. The team celebrated, but here's what really gets me. They just extended Voyager 1's life by another 2 to 3 years with this single decision. 2 to 3 years of extra science, extra discoveries, extra data from interstellar space, all because someone asked, "What if we try the old thrusters?" And it worked. They did the same thing with Voyager 2 in 2019, switching to its backup thrusters after 37 years. And again, it worked perfectly. This tells you something about how well these spacecraft were built. Components designed to work for 5 years are still functioning after 47 years in the harshest environment imaginable. But the most heartbreaking decisions aren't about fixing things, they're about choosing what to kill. Because Voyager's power is dying. The RTGs lose about 4 watts per year as the plutonium decays. In 1977, Voyager had 470 watts to work with. Today, about 220 watts and falling. Every year, the team has to decide what to turn off to keep the most critical systems running. 2019, they shut down the heater for the cosmic ray subsystem. The instrument is now operating at 79 degrees Celsius, far below its designed operating temperature of 49 degrees, but it's still working, still sending data. 2020, another heater shut down, this time for the low-energy charge particle instrument. Temperature drops to 85 degrees, still working. 2021, they turned off the heater for one of the attitude control thrusters. They're gambling that the fuel won't freeze, and so far they're right. Each decision is agonizing. The team knows these instruments weren't designed to operate this cold. They're essentially freezing Voyager to death, one component at a time, to keep it alive a little bit longer. It's like an elderly person in a cold house turning off the heat in the bedrooms to save enough money to keep the living room warm. And there's a clock ticking. By current estimates, Voyager will reach a critical power threshold around 2025 to 2030, the point where it can no longer run even a single science instrument and keep the transmitter working. When that happens, they'll have to start shutting down science instruments permanently, not just their heaters. Which one do you choose? The magnetometer that's measuring interstellar magnetic fields, the cosmic ray detector that's giving us unprecedented data about radiation in deep space, the plasma wave instrument that's detecting those mysterious density variations? Suzanne Dodd, the current project manager, was asked how she'll make these decisions. She said, "We'll follow the science. Whichever instrument is giving us the most valuable data, the most unique information we can't get anywhere else, that's what we'll keep until the very end." But she also said something that broke my heart. Every time we shut something down, it feels like losing a friend. They fixed it by sending a reset command to that specific memory location. It took weeks to isolate the problem and implement the fix, but they did it, and this is the terrifying reality. Cosmic rays are constantly bombarding Voyager. Most of them pass through harmlessly, but occasionally one hits just the wrong spot. And each time it happens, the team has to play detective from 15 billion miles away. There's also the deep space network problem, something most people don't think about. Voyager's signal is incredibly weak. When it reaches Earth, the signal is about 20 billion times weaker than a modern digital watch battery. To receive this whisper from interstellar space, NASA uses the Deep Space Network, 3 enormous antenna complexes located in California, Spain, and Australia, spaced around the Earth so that at least one is always facing Voyager. But these antennas are old. The 70-meter dishes were built in the 1960s. They're constantly breaking down, requiring maintenance, needing upgrades. When the Australian antenna went offline in 2020 for 11 months, Voyager 2 was completely cut off because it's in a region of the sky only visible from the southern hemisphere. The engineers lived in fear that Voyager 2 would have a crisis during those 11 months, and they'd be helpless to respond. And here's a logistical nightmare that keeps getting worse. Tracking time. Every antenna in the Deep Space Network is in high demand. Multiple missions need communication time. Mars rovers, asteroid missions, other deep space probes. Voyager has to share antenna time with all of them, but as Voyager's power decreases and its signal gets weaker, it needs longer tracking sessions to receive the same amount of data. Currently, Voyager needs about 12 hours of tracking time per day to download its science data. By 2030, it might need 18 to 20 hours. Where does that time come from when the antennas are already overbooked? There's a very real possibility that Voyager won't die because it runs out of power. It'll effectively die because we can't afford the antenna time to listen to it anymore. Imagine that. A spacecraft still functioning, still trying to talk to us, but we're too busy to listen. That would be a tragedy beyond measure. Now, let me share something that very few people know about. The Voyager team itself. There are currently about 12 full-time engineers managing both Voyager spacecraft. 12 people. That's it. Some of them have been working on Voyager for 30, 40 years. They started as young engineers, fresh out of college, and now they're approaching retirement, still caring for these ancient machines. I spoke to someone who knows one of the engineers, and they told me something beautiful. This engineer has a photo of Voyager 1 on his desk. Not a NASA official photo, but a photo he took of his computer screen in 1979 when the Jupiter images were coming in. He's kept that photo for 45 years. He comes to work every day knowing that one day, probably soon, he'll come in and Voyager will be silent. And when that happens, a piece of his life, a piece of his identity, will end with it. These engineers have developed an almost parental relationship with Voyager. They talk about teaching it new tricks, helping it through hard times, making it comfortable as it ages. They've created new software routines to compensate for failing hardware. They've figured out how to operate instruments at temperatures that should destroy them. They've invented workarounds for problems that the original designers never anticipated. There's a philosophy embedded in the Voyager team that I find deeply moving. It's called, keep them alive one more day, not one more year, not one more mission milestone, one more day. Every morning, the team comes in with the goal of keeping Voyager functioning for just 24 more hours. And then the next day, they do it again and again. It's been 47 years of just one more day, and it's worked. But here's the question that haunts everyone. When do you let go? When do you stop fighting to keep a dying spacecraft alive? Because there will come a point where the power is so low that Voyager can't run any science instruments, can't send back any useful data. It'll just be a carrier signal saying, I'm still here, growing weaker and weaker. Do you keep listening to that signal until it fades to silence? Or do you turn off the last instruments, send one final command, and say goodbye while Voyager can still respond? The team has discussed this. Some want to keep listening to the carrier signal as long as possible, even with no science data, just to know Voyager is out there. Others feel that once the science ends, the mission should end with dignity. One final transmission, one last acknowledgement, and then silence on our end, letting Voyager drift into eternity without us constantly calling out to it. I don't know which is right. Both feel heartbreaking in different ways. There's one more crisis I need to tell you about because it perfectly captures the ingenuity of this team. In 2002, Voyager 1's star tracker, the instrument that identifies stars to determine spacecraft orientation, started malfunctioning. Without it, Voyager couldn't accurately point its antenna at Earth. The team realized the star tracker was being confused by cosmic rays creating false stars in its field of view. The solution was brilliant. They reprogrammed the spacecraft to compare its star tracker data with its gyroscope data. If the star tracker saw something the gyroscope said wasn't there, ignore it. They turned a single sensor into a double-check system, using 1970s technology to create a redundancy that didn't originally exist, and it's still working today, over 20 years later. This is what I mean by teaching old dogs new tricks. Voyager is doing things it was never designed to do, operating in ways its creators never imagined, because a small team of dedicated engineers keeps finding creative solutions to impossible problems. They're not just maintaining a spacecraft, they're performing a kind of magic, keeping something alive through sheer determination and cleverness. But all of this, the crisis management, the creative problem solving, the desperate power budgets, raises a larger question about legacy. Because Voyager isn't just a spacecraft anymore, it's become a symbol, a cultural icon, a representative of human ambition and curiosity. The way people talk about Voyager, the emotions it evokes, the meaning it holds, that's something the engineers who built it never anticipated. And understanding what Voyager has become to our culture, how it's influenced art and music and philosophy, how it's changed the way we think about exploration and mortality and meaning, That's a story worth exploring as we approach the inevitable end of this mission. In 1986, a science fiction writer named Arthur C. Clarke was asked what humanity's greatest achievement had been in the 20th century. People expected him to say the moon landing, or perhaps the invention of the computer. Instead, he said something that confused the interviewer: the Voyager Golden Record. Not the mission itself, not the discoveries, the record. When pressed to explain, Clarke said, landing on the moon was about conquest, about winning a race. The Golden Record was about hope. It was about believing that we matter enough to introduce ourselves to the universe, even though we'll never know if anyone is listening. That kind of hope, that kind of belief in meaning despite uncertainty, that's what separates us from animals. That's what makes us human. And in that moment, Voyager stopped being just a space mission and became something else entirely. A mirror that shows us who we want to be, even if we're not there yet. If you want to understand how two machines launched in 1977 became cultural icons that influenced everything from blockbuster movies to bedside prayers, and why people who've never met the engineers cry when they think about Voyager going silent, this is a story about why we need symbols of transcendence. And if this resonates with your own search for meaning, let me know by hitting that like button. Let me start with something most people don't know: Star Trek. The entire Star Trek franchise, from The Next Generation onward, has been directly influenced by Voyager. The creator Gene Roddenberry kept a model of Voyager in his office. When he was developing The Next Generation in 1987, he told the writers, "I want our starship to be like Voyager, going further than anyone has gone before, encountering the unknown, representing the best of humanity even when we're far from home." The opening narration, "to boldly go where no one has gone before," that's Voyager's mission statement. The whole concept of the Enterprise is a peaceful explorer rather than a warship. That comes directly from the Voyager philosophy. And here's what gets me. In the Star Trek Voyager series that ran from 1995 to 2001, the ship is literally named after the probe. The premise, a starship thrown 70,000 light years from home, trying to get back to Earth, is a direct metaphor for Voyager 1 and 2, traveling beyond the solar system, sending messages home, never to return. The show's creator, Jerry Taylor, said in an interview, "Voyager the spacecraft inspired Voyager the show because it embodied something essential about the human spirit, the willingness to keep going even when you can't go home." But Voyager's cultural impact goes way beyond Star Trek. In 2017, a symphony orchestra in London performed the Voyager Symphony, a 90-minute piece composed specifically to accompany the journey of Voyager through space. The composer, Vangelis, who also scored Blade Runner and Chariots of Fire, said he'd been thinking about Voyager for decades. The symphony has no traditional structure. It's meant to represent the loneliness, the vastness, the slow passage of time. When it premiered, audience members reported feeling overwhelmed, some crying, not because the music was sad, but because it made them feel the scale of what Voyager represents. Then there's the visual art. In 2013, an artist named Trevor Paglen collaborated with NASA to create The Last Pictures, a disc similar to the Golden Record, attached to a communication satellite, containing 100 photographs meant to last billions of years after humans are gone. When asked why he created it, Paglen said, "The Golden Record changed how I think about time and legacy. Most art is created for audiences that exist now, but Voyager's record was created for an audience that might never exist, in a future we can't imagine. That's the most ambitious art project in human history, and it made me want to create something similar." There's a movement now among artists called deep time art. Art created not for contemporary audiences, but for civilizations thousands or millions of years in the future. Every single project cites Voyager's Golden Record as inspiration. These artists are asking, what do we want to say to a future that won't remember us? What's worth preserving when everything else fades? These are questions that didn't really exist in mainstream art before Voyager. But here's where Voyager's cultural impact gets really interesting. Religion and spirituality. There are people who pray to Voyager, not literally worship it as a god, but use it as a focus for meditation about humanity's place in the cosmos. I know this sounds strange, but hear me out. In Japan, there's a Buddhist temple that added Voyager to its prayers in 1990. The priest explained, "We pray for all beings to be free from suffering. Voyager is the loneliest being humanity has created, separated from everything it knows, traveling alone forever. Its loneliness reminds us of our own isolation, and praying for Voyager is a way of acknowledging that suffering and seeking compassion for it." In 2012, when Voyager 1 crossed into interstellar space, over 400 churches, temples, and mosques around the world held services marking the occasion. Christian churches framed it as humanity fulfilling the biblical mandate to fill the earth and subdue it, extending our reach into creation. Islamic scholars talked about how Voyager demonstrates humanity's role as Khalifa, stewards of knowledge, exploring Allah's creation. Hindu temples discussed Voyager in the context of cosmic consciousness, the idea that all of reality is one interconnected whole, and Voyager extends that connection. I'm not saying Voyager is a religious object, but it serves a religious function for many people. It's a symbol of transcendence, of reaching beyond our limitations, of creating meaning in a universe that doesn't hand us meaning. And that's powerful. Now, let me tell you about the personal stories, because these are what really break my heart. There's an engineer named Ed Stone who's been Voyager's project scientist since 1972, before the spacecraft even launched. He's 88 years old now. He's dedicated 52 years of his life to this mission. That's longer than most marriages. That's longer than most careers. In a 2022 interview, he was asked, "What will you do when Voyager goes silent?" He started to answer, then stopped, and you could see him fighting back tears. Finally, he said, "I don't know. I've never had to think about a world where Voyager isn't talking to us. It's been the constant in my life, my marriage, my children, my career. Voyager has been there through all of it, always steady, always sending data. When it stops, I think a part of me will stop too." There's a woman named Candy Hansen who worked on Voyager's imaging team from 1977 to 1989. She was 26 when Voyager launched, 38 when it flew by Neptune. She left NASA after Neptune to start a family, moved away from space science entirely. But she told an interviewer that not a week goes by where she doesn't think about Voyager. She keeps a framed photograph from the Neptune encounter on her wall, not an official NASA photo, but a printout from the actual data stream as it came in, with her handwritten notes in the margins. She said, "Those 12 years were the most alive I've ever felt. Every day was discovery. Every day mattered. I've had a good life since then, but nothing has ever matched the feeling of watching those images come in, knowing we were seeing things no human had ever seen. Voyager gave me a standard for what meaningful work feels like, and everything else has been a little bit disappointing in comparison. This is what I want you to understand. Voyager hasn't just been a mission for the people who worked on it. It's been the central organizing principle of their lives, the thing that gave them purpose and identity. And when it ends, they'll have to figure out who they are without it. But it's not just the engineers. There are people around the world who have followed Voyager their entire lives. There's a man in Brazil who's been tracking Voyager's position every single day since 1989, 35 years. He maintains a website that shows exactly where Voyager is, what it's seeing, what its power levels are. When asked why he does this, he said, "Because someone should be paying attention. Someone should be witnessing this journey. If I stop watching, if everyone stops watching, it's like Voyager's journey doesn't matter. So, I watch." There's a group in Australia that holds an annual Voyager Vigil on the anniversary of the launch. They gather with telescopes, even though Voyager is far too small to see. and they point their telescopes in the direction where Voyager is, and they stay up all night sharing stories about what Voyager means to them. It's like a secular religious ceremony, a way of acknowledging that something greater than themselves exists out there in the dark. And then there are the children. Entire generations have grown up knowing about Voyager. Teachers use it in classrooms as an example of human achievement. Parents tell their kids about Voyager when teaching them about perseverance, about not giving up even when things are hard. There are people who, when they're going through difficult times, think about Voyager, alone, freezing, running out of power, 15 billion miles from home, and they think, if Voyager can keep going, so can I. I know that sounds melodramatic, but I've read hundreds of letters sent to NASA about Voyager, and this theme comes up over and over. Cancer patients who think about Voyager during chemotherapy. Students struggling with school who remind themselves that Voyager kept working when most of its systems failed. People in toxic relationships who finally leave because they think, Voyager had the courage to go into the unknown, so can I. Voyager has become a symbol for anyone who feels alone, who feels like they're on a journey with no clear destination, who feels like they're operating in conditions they weren't designed for. And that's almost everyone at some point in their lives. Here's a question for you. What symbol or story do you return to when you need inspiration to keep going? Drop it in the comments. I'm genuinely curious. But there's a darker side to Voyager's cultural impact that we should acknowledge. Some people have become almost obsessed with it in unhealthy ways. There are individuals who talk about Voyager like it's a person, who become genuinely depressed thinking about its eventual silence, who have built their entire identities around this spacecraft. Psychologists have written about Voyager attachment syndrome, not a real clinical diagnosis, but a pattern they've observed where people become emotionally dependent on the idea of Voyager as a source of meaning in their lives. One therapist I read about works with several clients who have this pattern. They check Voyager's status multiple times a day. They have anxiety attacks thinking about it going silent. They've told their therapist that they're more worried about Voyager dying than about their own mortality. The therapist's take is interesting. She says, Voyager represents the possibility of permanence in a temporary world. Everything in our lives ends, relationships, careers, life itself. But Voyager, flying through space forever, even after it goes silent, offers a kind of immortality that we can't have ourselves. People latch onto it because it's easier to invest in Voyager's survival than to confront their own fears about impermanence. I think there's something to that. Voyager is still out there, still moving, and it will keep moving for billions of years after everything we know is gone. In a weird way, Voyager is the closest thing to eternal that humanity has created. And for people struggling with mortality, with the meaninglessness that sometimes accompanies existence, Voyager offers proof that we can create something that lasts. But let's talk about the lessons Voyager teaches about doing meaningful work, because I think this is where its cultural impact is most profound. Voyager was built by people who knew they'd never see the end of the mission. The engineers who designed it in the 1970s knew that if it succeeded, it would outlive them. They were working on something they'd never see completed, and yet they gave it everything they had. This is increasingly rare in modern culture. Most work is designed for immediate results. Build an app, see if it succeeds in 6 months. Create content, measure the views this week. Launch a product, know within a quarter if it's profitable. We've lost the art of long-term thinking, of building things that won't pay off until after we're gone. Voyager is a rebuke to that short-term thinking. It says, some things are worth doing even if you'll never see the outcome. There's a story about one of the engineers who welded parts of Voyager's chassis in 1976. He was interviewed in 2012 when Voyager crossed into interstellar space. He was 82 years old, retired for 20 years. And he said something that stuck with me. I welded thousands of parts in my career. Most of them are in landfills now, or junkyards, or they broke and were replaced. But somewhere out there, 11 billion miles away, my welds are still holding. The parts I joined in 1976 are still together, still strong, still doing their job. That's what I think about when I wonder if my life mattered. I built something that outlasted me. That's legacy. Not fame, not wealth, but contribution to something larger than yourself. And Voyager offers that to everyone who worked on it, a sense that they were part of something that will echo through time long after they're forgotten. But here's what really gets me about Voyager's cultural legacy. It's inspired other missions, other acts of exploration, in ways both direct and subtle. The New Horizons mission to Pluto, launched in 2006, was directly inspired by Voyager. The lead scientist, Alan Stern, has said repeatedly that Voyager proved we could explore the outer solar system, and that inspiration led to New Horizons. The Parker Solar Probe, launched in 2018 to study the Sun up close, carries similar durability philosophy. Build it to last in extreme conditions, over-engineer everything, plan for the unexpected. That's pure Voyager thinking. Even SpaceX's Starship program has echoes of Voyager. Elon Musk has talked about making humanity multi-planetary, about sending ships to Mars that might never return, about building things that will outlast their creators. He's never directly cited Voyager as inspiration, but the philosophy is identical. Do something so ambitious that its completion is uncertain, and do it anyway, because the attempt itself has value. Voyager changed the conversation about what's possible. Before Voyager, space exploration was about flags and footprints, about winning races and claiming territory. Voyager shifted it toward exploration for its own sake, toward knowledge as a worthy goal, independent of political or economic return. You can see that shift in how we talk about space now. We don't talk about conquering Mars. We talk about exploring it, understanding it, learning from it. That's Voyager's linguistic legacy. There's also an entire generation of scientists and engineers who went into their fields because of Voyager. They saw those images of Jupiter, Saturn, Uranus, Neptune, and they thought, I want to be part of that. I want to discover things no one has seen before. Surveys of planetary scientists show that about 40% cite Voyager as a major influence on their career choice. Think about that. 4 out of 10 people studying planetary science today are doing so because Voyager inspired them. The mission hasn't just explored space, it's populated the field with people who will continue that exploration. And here's something beautiful. Voyager has become a common reference point across cultures in a way that almost nothing else has. In countries that don't agree on politics, religion, history, or values, people still agree on Voyager. It's politically neutral. It's not American or Soviet or Western or Eastern. It's human. There are Voyager exhibits in museums in Beijing, Moscow, Paris, Johannesburg, São Paulo, everywhere. And in all of them, the message is the same. We did this, all of us, as a species. In a world that feels increasingly divided, increasingly tribal, Voyager offers a rare moment of unity. We can disagree about everything else, but we can agree that sending these spacecraft to explore the cosmos was a good thing, a worthy thing, a human thing. But we need to be honest about something. Voyager's cultural impact is largely limited to people who already care about space, science, and exploration. Most people, if you ask them about Voyager, have maybe heard the name but don't know what it is. It hasn't penetrated popular consciousness the way the moon landing did. And there's a lesson in that about how we value different kinds of achievement. The moon landing was visible, immediate, dramatic, perfect for television. Voyager is slow, patient, undramatic, terrible for television. We're better at celebrating spectacle than we are at celebrating persistence. And yet, for those who do know the story, Voyager holds a place that the moon landing doesn't. The moon landing was a moment. Voyager is an ongoing saga, a decades-long story of perseverance and discovery. You can't binge-watch Voyager. You have to live with it, year after year, watching it slowly drift further from home. That temporal investment creates a different kind of connection. It's not excitement, it's companionship. Voyager becomes part of your life in a way that single dramatic events don't. So, what happens when Voyager goes silent? What happens to its cultural legacy when there's no more new data, no more crises to solve, no more discoveries to celebrate? Does it fade into history, becoming a footnote in textbooks? Or does it take on new meaning, the way historical events sometimes become more significant after they end? I think, and this is speculation, but informed speculation, that Voyager's cultural impact will actually grow after it goes silent. Right now, it's an active mission. It's still working, still sending data. But when it stops, when that final transmission is sent and there's no response, it becomes something else. It becomes a monument, a memorial, a time capsule. And humans are very good at investing meaning in monuments. The Voyager spacecraft will keep flying for billions of years. Long after Earth is gone, long after the sun has died, Voyager will still be out there, carrying its golden record, drifting through the galaxy. That's not just impressive, it's profound. It means that the last surviving evidence of our existence might be these two machines and their messages. And that thought, that possibility, will haunt human consciousness for as long as humans exist. We'll look up at the stars and know that somewhere out there, our message is still traveling, still waiting to be found, still representing who we were at our best. But all of this cultural meaning, all of this legacy and inspiration and symbolism, it all depends on one final act. The moment when Voyager sends its last transmission and falls silent. How we handle that moment, what we choose to do and say as Voyager dies, will determine how it's remembered for generations to come. And that's a responsibility that weighs heavily on everyone involved, because getting it right means honoring not just the machine, but everything it represents about who we are and who we aspire to be. There's a file sitting on a computer at NASA's Jet Propulsion Laboratory. It's labeled Voyager Final Sequence. Inside that file is a series of commands that have been carefully written, reviewed, and revised over the past decade. These commands have never been sent. They sit there, waiting, like a letter you've written but haven't mailed yet. Because once these commands are sent, once Voyager executes them, that's it. The mission is over. The conversation ends. And here's what haunts everyone who knows about this file. They don't know when they'll have to open it. Could be 2025. Could be 2030. Could be next week if something catastrophic fails. Every engineer who works on Voyager knows that one day, maybe soon, they'll come to work and someone will say, "It's time. We need to send the final sequence." And everything they've fought for, everything they've dedicated their lives to preserving, will come to an end. If you want to understand what happens when we say goodbye to something that can never say goodbye back, and why that final moment might be the most important transmission Voyager ever sends, stay with me until the end. Because what I'm about to share will change how you think about endings, about legacy, and about what it means to create something that outlives you. And if this journey through Voyager's story has moved you, one last like would mean the world. Let me tell you what's in that final sequence, because it's both beautiful and heartbreaking. The commands are designed to do several things in order. First, Voyager will use whatever power it has left to orient itself one final time toward Earth. It will point its antenna as precisely as possible, giving us the clearest signal it can manage. Then it will transmit a data package containing every bit of information stored in its memory, a complete record of its journey, its discoveries, its status, everything. Think of it as Voyager's last will and testament, a final summary of 50+ years of exploration. After that, the sequence commands Voyager to activate all of its remaining scientific instruments simultaneously, even though this will drain the power faster. Why? Because the engineers want one final burst of data from interstellar space, one last comprehensive snapshot of conditions out there. It's Voyager going out, not with a whimper, but with everything it has left to give. Then comes the part that makes me cry every time I think about it. The final sequence includes a command for Voyager to transmit a specific message back to Earth. Not data, not scientific measurements. A message. The exact content is classified. NASA hasn't made it public because they don't want it to lose its impact when the moment comes. But people who've seen it say it's a simple statement, maybe just a few words, acknowledging the end of the mission. Some speculate it might be something like "mission complete," or "thank you for listening," or just "goodbye." And then, after that message is sent, Voyager will shut down its transmitter, not because it's been commanded to, but because it won't have enough power to keep it running. The last thing we'll receive is that message, and then silence, forever. Susan Dodd, the project manager, was asked in a 2023 interview how she's preparing for that moment. She said something that broke my heart. "You can't prepare for it. I've been working on Voyager for 23 years. I've spent more time talking to these spacecraft than I've spent talking to some members of my family. And I know that one day I'm going to send a command and get no response. And that will be the worst day of my professional life. Maybe my personal life too. How do you prepare for that? You don't. You just brace yourself and hope you can get through it with some dignity. But here's what's interesting. Not everyone at NASA agrees on when to send that final sequence. There's a debate happening right now about the criteria for ending the mission. One camp says, as long as Voyager can send any signal, even just a carrier tone with no data, we should keep listening. Every additional day we receive that signal is a victory, proof that we built something that refuses to die. The other camp argues that once the scientific instruments shut down, once there's no more data coming back, the mission should end with dignity. Send the final sequence while Voyager can still respond meaningfully, rather than waiting for it to fade into incomprehensible static. Ed Stone, the chief scientist, is in the first camp. He wants to listen to Voyager's carrier signal until it's absolutely gone, even if it's sending nothing but "I'm still here" for months or years. His argument is simple. We sent these spacecraft to go as far as possible and report back for as long as possible. Until the last electron leaves that transmitter, Voyager is still fulfilling its mission. Others feel this is selfish, that we're keeping Voyager on life support for our own emotional needs, rather than letting it end with purpose. One engineer told me, "If my dad were dying, and doctors said they could keep his heart beating, but he'd be unconscious, unable to communicate, just existing without awareness, I'd want to let him go with dignity." That's how I feel about Voyager. When the science ends, the mission should end. I don't know who's right. Both perspectives honor Voyager in different ways. But let's talk about what happens after that final transmission, because this is where the story gets truly cosmic in scale. The moment Voyager's transmitter shuts off, the spacecraft becomes something different. It stops being a mission and becomes an artifact, a time capsule, a monument flying through space at 38,000 miles per hour, forever. And when I say forever, I mean it literally. Voyager will keep moving through space for billions of years. Let me give you the timeline, because it's almost incomprehensible. Year 40,272 AD, 38,000 years from now. Voyager 1 will pass within 1.6 light-years of the star Gliese, 445. If there are planets orbiting that star, if there's anyone there to see it, Voyager will be a brief visitor, a shooting star carrying a message from a world they'll never know. Year 296,036 AD, 294,000 years from now. Voyager 2 will pass within 3 light-years of Sirius, the brightest star in Earth's night sky, the Dog Star. By this time, human civilization will either be unrecognizably advanced or extinct. Either way, Voyager will still be flying. And then, Voyager will orbit the center of our galaxy every 225 million years, forever. Or until something destroys it. A collision with a dust grain traveling at relativistic speeds, or getting caught in a star's gravity, well, billions of years from now. But absent that, Voyager is essentially immortal. Think about what this means. 5 billion years from now, our sun will swell into a red giant and consume the Earth. Everything we've ever built, every city, every monument, every work of art, every book, every digital file, gone, vaporized. The only surviving evidence that humanity existed might be Voyager and its golden record, drifting in the dark, carrying sounds and images of a world that no longer exists. Carl Sagan wrote about this possibility, and his words haunt me. The spacecraft will be encountered and the record played only if there are advanced spacefaring civilizations in interstellar space. But the launching of this bottle into the cosmic ocean says something very hopeful about life on this planet. Even in our current difficulties, we were able to think of the welfare of a civilization 10,000 years in the future, one that may never know of our existence. That last part, one that may never know of our existence, that's what gets me. We created something for an audience that will probably never exist, carrying a message that will probably never be received. And we did it anyway. Because the act of reaching out, the act of saying, we were here, we mattered, we cared enough to try, that act has value independent of outcome. But I want to challenge something that I've heard repeated many times. The idea that Voyager represents humanity at its best, that it's a pure expression of our noblest qualities. Is it though? Let's be honest. Voyager was born out of Cold War competition. It was funded because politicians wanted to beat the Soviets, wanted to plant America's flag, metaphorically, on the outer planets. The science was secondary to the politics. The golden record was added almost as an afterthought, a pet project that NASA barely tolerated. And Voyager's journey hasn't been a story of unity and cooperation. It's been a story of struggle, of fighting for resources, of having to justify its existence year after year to bureaucrats who didn't care about interstellar space when there were budget shortfalls to manage. The mission has survived not because humanity valued it, but because a small group of dedicated people refused to let it die, often against institutional resistance. So maybe Voyager doesn't represent humanity at its best. Maybe it represents humanity as we actually are, flawed, conflicted, motivated by mixed intentions, but capable of creating something greater than our limitations, capable of starting a project for the wrong reasons and continuing it for the right ones, capable of building something that outlasts our pettiness and our politics. There's a lesson in that about legacy. We don't have to be perfect to create something perfect. We don't have to have pure motivations to achieve pure results. Voyager was built by flawed people in a flawed system for partially flawed reasons, and it's still the most beautiful thing humanity has done. That should give us hope. It means we don't have to wait until we've solved all our problems, until we've become better versions of ourselves, to do meaningful work. We can start now, as we are. Now, let me tell you about a conversation I had. Well, someone told me about a conversation they had with one of the engineers who's preparing for the final transmission. He's in his 60s, been working on Voyager for 35 years, and he said something that stuck with me. He said, "People ask me if I'm afraid of Voyager dying, and I tell them no, I'm not afraid of Voyager dying. I'm afraid of Voyager being forgotten. Because as long as someone remembers Voyager, as long as someone tells its story, the mission doesn't really end. It transforms into something else, a myth, a legend, an inspiration. But if everyone forgets, if the story disappears, then Voyager truly dies, even though the spacecraft is still out there flying. And that's on us. That's on everyone who's heard this story, who's felt something listening to it. We have a responsibility to remember, to tell others, to keep Voyager alive in human consciousness, even after it stops sending data. Because that's how legacy works. It's not automatic. It requires active participation from each generation, choosing to value what came before, choosing to carry that torch forward. Let me ask you, what will you do with this story? Will you share it? Will you tell someone about Voyager who's never heard of it? Will you remember it 10 years from now, 20 years from now, when the final transmission has been sent and Voyager is just a memory? Because that's how we honor the people who built this, who dedicated their lives to keeping it alive. We remember, we pass it on. There's something else I need to say about endings, because Voyager's approaching end is teaching us something important about how we handle mortality, both of machines and of ourselves. We live in a culture that's terrified of endings. We don't want to talk about death. We don't want to acknowledge that things end. We constantly distract ourselves from the reality of impermanence. But Voyager is forcing us to confront it. The engineers working on Voyager can't pretend it will last forever. They know it's dying. They watch its power levels drop year by year. They make decisions about what to sacrifice to extend its life a little longer. And in doing so, they're modeling something important: how to let go with grace, how to fight for every extra day while also accepting that the end is coming, how to celebrate what was achieved rather than grieving what will be lost. That's a lesson all of us need, because everything ends. Relationships end, careers end, lives end. And we can either spend our time in denial, pretending endings don't exist, or we can learn from Voyager, keep going, keep contributing, keep creating value right up until the last moment, and then let go, knowing we gave everything we had. There's a specific moment I keep thinking about. Someday, probably within the next 5 years, an engineer at JPL is going to send a command to Voyager. They'll wait 22.5 hours for a response, and there will be no response. They'll try again. Still nothing. They'll check the equipment, run diagnostics, verify that their own systems are working. Everything will be fine on Earth's end, which means the silence is coming from Voyager. It's gone. And then that engineer will have to stand up, walk down the hall, and tell their colleagues, "I think this is it. I think we just lost Voyager." There will be a meeting. They'll try to confirm it, send more commands, wait longer, but eventually they'll have to accept it. Voyager 1 or Voyager 2 has stopped responding. The mission is over. What happens next? I imagine there will be tears, a lot of tears. Then someone will send out an email to the Voyager team, past and present. Then a press release will go out to the world. After X years of operations, NASA has lost contact with Voyager 1 and 2. The spacecraft is believed to have exhausted its power supply. This marks the end of humanity's longest and most distant space mission. News outlets will cover it, social media will briefly mourn, and then life will go on. Most people will move on to the next story. But for the people who worked on Voyager, for the people who followed its journey, for the people who found meaning in its story, something will have changed. A light will have gone out. Not in space. Voyager will still be there, still flying, but in us. The light of connection, the feeling of being linked to something out there in the dark, that light will go out. And we'll have to learn to live in a world where Voyager is no longer calling home. But here's what I want you to take away from this entire story. Voyager's final transmission won't be its last message. The last message is the one we're living right now, the one that will continue after Voyager goes silent. Because Voyager's real message was never about Jupiter's clouds or Saturn's rings or the temperature of interstellar space. The real message was this: you can create something bigger than yourself. You can contribute to knowledge that outlasts you. You can start a journey that others will continue after you're gone. Every person who worked on Voyager, from the engineers who welded its parts to the scientists who interpreted its data to the programmers who wrote its code, they all knew they were part of something that would outlive them. And they chose to do excellent work anyway, knowing they'd never see the full impact of what they created. That's nobility. That's meaning. That's how you live a life that matters. And you don't need to build a spacecraft to do it. You can teach a student who will go on to do great things. You can plant a tree that will shade people you'll never meet. You can create art that will move someone 50 years from now. You can raise children who will change the world. Legacy isn't about fame or wealth. It's about contributing something of value that continues after you're gone. Voyager is teaching us that the goal isn't to live forever. It's to build something that does, to create meaning that transcends our brief existence, to reach out into the darkness and say, I was here, and I tried to make something beautiful. That's what Voyager did, and that's what we can all do in our own ways, in our own time. So, when Voyager goes silent, when that final transmission is sent or fails to arrive, I don't want us to mourn only what we're losing. I want us to celebrate what we gained. 50 years of discoveries, 5 planetary encounters that changed how we see the solar system, the pale blue dot photograph that changed how we see ourselves, the golden record that represents our best hopes for who we could be, 2 spacecraft that will carry our message through the cosmos long after we're gone. That's not a tragedy. That's a triumph. That's humanity saying to the universe, we're small, we're flawed, we're brief, but we mattered. We were here, and we reached out. And when I lie down at night, when I close my eyes and think about Voyager out there in the dark, 15 billion miles from home, still sending its signal, still doing its job, still refusing to quit, even though every reason says it should, I feel something that's rare in this cynical age. I feel hope. Hope that we can be better than we are. Hope that our best qualities, curiosity, perseverance, the desire to explore and understand, can overcome our worst qualities. Hope that what we create with love and dedication can outlast our failures and our flaws. Voyager is a promise we made to the future. A promise that we cared enough to reach out, to explore, to try to understand the cosmos we're part of. And even though Voyager will soon go silent, that promise lives on. In every scientist it inspired, in every child who looked up at the stars and wondered, in every person who heard the story and felt that spark of possibility. The final transmission, when it comes, won't be an ending, it'll be a transformation. Voyager will stop being a mission and become a legend. And legends, unlike machines, can live forever, as long as we keep telling the story. Thank you for taking this journey with me. Thank you for caring about 2 spacecraft launched almost 50 years ago by people who dared to dream bigger than their limitations. Thank you for remembering that we're capable of extraordinary things when we commit to something larger than ourselves. And remember, Voyager's message isn't just traveling through space, it's traveling through time, through you. Every time you share this story, every time you're inspired to create something that will outlast you, every time you choose perseverance over surrender, you're continuing Voyager's mission. You're keeping that signal alive. Keep exploring, keep creating, keep reaching out into the darkness because you have to know what's there. That's the Voyager spirit. And it doesn't end when the spacecraft goes silent. It ends when we stop trying. We'll be back with more cosmic stories that will change how you see the universe and your place in it. Until then, keep looking up, keep wondering, and keep believing that what you create today can echo through eternity. Sweet dreams, fellow travelers, and may your journey be as bold and beautiful as Voyager's.